Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the part 2 of our PYQ series of control system. So in the part 1 we have already discussed about the time domain parameters, basics of control systems, SFG also we have discussed in a great manner. Now in this lecture there will be two chapters, Routh-Hurwitz RH criteria and the second chapter, that is root locus. These two chapters are also very important. Okay, so don't neglect this, and this will be utilized in frequency response. So if you don't understand here, you'll not be able to understand the frequency response. So watch this video, enjoy this video, and if you are enjoying, so just one thing, like the video. Okay, comment down below if you are learning the things, if you are able to pick up the things without even like if you have already studied for some other place XYZ, whatever it may be, and you are studying here, and if you are able to understand, please do comment down below, because it will help us to reach other students. Other students also will understand this. Okay, we are teaching something great. Trust me, right? Once you will study the RH criteria and the root locus, you will understand, like there will be very small things that I will tell you to memorize. Most things you will understand intuitively. Intuitively I will explain, I will solve all the questions. You can see the solutions of the gate PYQs. There I have used very little calculation. Mostly we have solved using intuition. So yeah, let's start with RH criteria. So let's begin with Routh-Hurwitz criterion. So first of all, we will discuss what does Routh-Hurwitz criterion help us to achieve. So in the previous series, right, previous part, we discussed, like I talked to you with regarding the stability. I told you, okay, this is not stable. Poles are lying on the right hand side. The system is not stable, and I did some calculations, right? And there I told you that we will learn that in the next chapter. So Routh-Hurwitz criterion is helpful for determining the absolute stability. What do you mean by absolute stability? Absolute meaning either the answer will be yes or no. Is the system stable? Yes or no. There is one more thing known as relative stability. So there is no direct answer. If there is a criteria, right, that we will learn in frequency response, that discusses regarding the relative stability in polar plot. There, right, we directly will not be able to say, if I have been given a characteristics equation, that whether the system will be stable or not, like yes or no, I cannot say. I will give some parameters that this is the gain margin of this system, this is the phase margin. With this we can deduce it is margin, it is what do you say, conditionally stable, or we will say it is relatively stable. We cannot comment about absolute stability, right? Absolute meaning which is certain in life. You can 100% guarantee that it is true, but relative meaning I cannot guarantee 100% it will be true, it may be false as well, but most of the times it is true. That is a part. So Routh-Hurwitz tells us absolute stability. Now your question might be, sir, then we should always use Routh-Hurwitz. Why do we learn in frequency response regarding the relative stability? Because this requires heavy computation. Although huge computation has been reduced right now, huge computation has been reduced, right? We will not calculate the location of poles. We can only comment whether my poles will lie on the right hand side or not. That's all. Although the calculation has been reduced, still there is some amount of calculation. And in frequency response, it is low. The calculation is lower. As the order of my transfer function increases, the calculation is much lower in frequency response than in Routh-Hurwitz. That's why we might prefer that method, because the calculation is lower. That is the single reason. I hope that part is clear by you. So if I have a simple polynomial, right, basically we will describe the right hand poles, right, and right hand poles are nothing but this equation. This equation is called as a characteristic equation, right? But Routh-Hurwitz can be used for any random equation. It's not like we can use Routh-Hurwitz only for characteristics equation. It can be used, this criteria can be used for any random equation, but in control systems we will mainly use it for the characteristic equation, because that equation tells us the location of poles of CLTF. That is the reason mostly we will use it for our characteristics equation. But Routh-Hurwitz criterion is a general criteria. It can be used for any polynomial, any equation, any polynomial equation. It has to be a polynomial equation. It cannot be this. That I will obviously discuss, that e raised to power as or e raised to power s plus 1 equal to 0. No, then Routh-Hurwitz will fail. We will have to use some approximation. Okay, so that is the thing basically. Routh-Hurwitz will be only used for general standard polynomial equation, any polynomial equation, but in control systems we will use it for the characteristics equation. So yeah, first of all we will discuss what is Hurwitz polynomial. A polynomial is said to be Hurwitz if all its roots have negative real part. So if I see here, right, this polynomial, so any polynomial, take the example n equals to 1 means n is basically the order of the polynomial, right, highest power. So n equals to 1, let me take a polynomial s plus 2 equal to 0. So this, right, I see that I have obviously s equal to minus 2. So one of the, I have one pole and that is lying on the left hand side of the j omega axis. So it is stable, no problems. Now what shall be the condition basically? So if I have another polynomial, let's say s minus 2, here I see the root is lying on the right hand side of the j omega axis, correct? Root is lying on the right hand side of the j omega axis. Now if I have another equation like minus s plus 2, here also I see root is lying on the right hand side of j omega axis, and if I have another equation, here I see root is lying on the, sorry, this here root is lying on the right hand side, here root is lying on the left hand side, this will be my left hand side. So what is the condition basically? Condition is basically, right, these two conditions, these two coefficients must be positive. So we only discuss about this whenever this is positive. We, of course, there is this condition as well, right, when both the coefficients will be negative. Yeah, so basically both the coefficients of my powers of s, right, both these coefficients, here this is s raised to power 0, this is also a power of s, this is s raised to power 0. Okay, so both these coefficients must be of same sign. If this is positive, this also has to be positive. So that is what my Hurwitz polynomial is. For a simple first order system, only we can check whether my roots will lie on the left hand side or not by checking the signs of polynomial. Okay, now even if one of the sign is changed, right, let's say if the signs are different, then it will not be a Hurwitz polynomial. Then just by looking at the equation, I can directly comment that it will have some roots that is on the right hand side. So first of all, we will check the condition of a polynomial being Hurwitz. If it is not Hurwitz, we will not go into Routh. Routh just modified this Hurwitz polynomial. Okay, so here what is the condition for Hurwitz polynomial? The condition for Hurwitz polynomial is that first of all, in a0 a1 both must be non-zero. Even if one of them is 0, then it is not a Hurwitz polynomial. So we will simply not check. What do I mean? So let's say I have this equation s cube plus s plus 1. Here, right, if I write this in proper format, this should be s cube plus 0 into s square plus s plus 1 equal to 0. Right, now I see one of the coefficients is 0 of s. So this is not a Hurwitz polynomial. So I can directly say that it will not be stable. We don't even need to check. Okay, so yeah, that is the thing. So if I have a second order polynomial, right, second order polynomial, all coefficients must be non-zero, all the coefficients must have same sign, then only it is a Hurwitz polynomial. So these are the conditions for being Hurwitz polynomial. First is it has to follow the rule for being Hurwitz polynomial. So for up until second order systems, right, up until second order system, if these two conditions are satisfied, then my system will be stable. Okay, anyways, we can easily find out the roots of a second order system, right? Now for polynomials of order 3, necessary and sufficient condition for them to be Hurwitz polynomial is that all coefficients must be non-zero and of same sign. Okay, so for third order system as well, all coefficients must be of same sign and they must be non-zero. But this is not the only condition for stability. There needs to be other conditions as well that has to be satisfied. So first of all, let us discuss here. Check whether these polynomials will be Hurwitz or not. Pause the video and try to work yourself. So here I see all of them are positive and all of the coefficients are non-zero. So this is a Hurwitz polynomial. Here I see all of the coefficients are positive, non-zero, Hurwitz polynomial. Here I see all the coefficients are not uh, positive here, right? Here I have a negative coefficient. So this is not a Hurwitz polynomial. So anyways, this is cancelled. Okay. Anyways, this is cancelled. Now one more thing is there, that okay, this is one of the condition, that all coefficient must be non-zero and of same sign. Okay. Sorry, here, right? Actually I discussed about for polynomials of order below 3. So basically not for order 3, I'm sorry, for polynomials of order till order 2. Okay, below 3 means till order 2. The condition for a polynomial to being Hurwitz is this, that all the coefficients must be non-zero and all of them must be of same sign. That is the only condition for it being to Hurwitz, and if it is Hurwitz, then all the poles will lie on the left hand side. If a polynomial is Hurwitz, then roots are like all the roots have negative real part, so all of them will lie on the left hand side. But as soon as I will come to order 3, you will feel like this is also a Hurwitz polynomial. No, the definition of Hurwitz polynomial for order 3 changes. So this is not Hurwitz anyways. I see that signs are not same, gone. This is Hurwitz. But this also will not be Hurwitz actually. Although it is satisfying these conditions, it is not Hurwitz. This was for till order 2. Now as soon as the order increases, then there are few more conditions that will be attached to it. Okay. So I think for polynomials of order 3 and more, a necessary condition for them to be Hurwitz is that all coefficients must be 0 and of same sign. But it is not sufficient. Here it was necessary and sufficient. This was enough. But this is not sufficient. Okay. For sufficiency, we have to construct Routh array. So then Routh came and Routh constructed his array, and by checking that condition, we can deduce whether the polynomial will be Hurwitz or not. So how to form a Routh table? So let me take a very basic example. Maybe I will have some. Okay, yeah. Here I have this basic example, right? So how to form the Routh array? So first of all, right, you have to write down your polynomial in proper format. So here, let's say this was s cube plus s square plus 3s plus 1. So I will first draw the table. I will write the highest order first. So s raised to power 3, s square, s raised to power 1, s raised to power 0. That's all, right? Till 0 I will go. Now I will write the coefficient of s cube here. So this will be 1. This will be 1. Now I will continue here till what point? So first I will write the coefficient of s cube, then I will skip s square and I will write the coefficient of s. S square coefficient will be here. Okay. So I will write the coefficient of s. So that will come here. Okay. Now I will again skip the coefficient of s raised to power 0, and I see there after s raised to power 0 there is nothing. So I will not write anything, right? Empty. Empty meaning it is 0. Empty meaning it is 0. Okay. I will write here 0, but empty meaning it is 0 simply, right? After this everything will be 0. Now I will write the coefficient of s square, that is 1, and then I will write the coefficient of s raised to power 0, that is 1. Again after that nothing is there, so I will write 0. Now these things I will have to calculate and fill up. So here, how do I calculate? So first what I will do, it is just like determinant. It is very similar to determinant. So first I will take this element, multiply with this, right? So 1 cross 3. And then I will multiply these two elements, 1 cross 1. 1 cross 3 minus 1 cross 1. I will subtract both of them and then divide by the element that is present over here from where I started. So this will be 3 minus 1 by 1. So that is 2. Okay. Now if I follow that process here, right, since I have 0 here, so it won't matter simply. All this will be 0 only. You will solve it, you will apply the same process, 1 into 0, 3 into 0, 0. Divide by 1, it is 0 only. So does not matter. Now what about here? Now as soon as you get a 0 here, right, simply you can copy this value here. I can show you the calculation as well. Simply I will do what? 2 into 1 minus 1 into 0, that is 0 only. So 2 into 1 divided by 2, that is simply 1. So that is a short trick that you can, like, it's a very easy thing to understand and remember, right? So simply if I have a 0 here, simply whatever element is at the top, that will be copied to here. Okay, and then this will be 0, 0. Now you have to be very careful with the first column. So that is the most important thing. Basically, like every element is important because ultimately this value is coming from the other elements only. So if I check the first column, if there is no change in sign of the first column, so if all of these values are positive, no change in sign, right? It is not like it has to be positive only. There must be no change in the sign. So this is positive. What is the sign of the first column? Positive, 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 positive. So there is no sign change. If there is no sign change, it will be a Hurwitz polynomial. And if it's a Hurwitz polynomial, then the system will be stable. That is how we describe the absolute stability. This is the method. That's it. This is your whole chapter. Okay, you're done. Your whole chapter is done. Of course, there are a few things that we will discuss. There are a few corner cases that we have to discuss. But mota mota yahi hai. Let's try to plot the Routh table for other polynomials as well. Like for b, s cube, s square, s plus 3. So let me first of all write the polynomial. S cube, s square, s plus 3. So this will be 1, 1. This will be 1, 3, s cube, s square, s raised to power 1, s raised to power 0. So yeah. So yeah, now again if you solve, I think this is not the same, this is just a little bit different. So here, right, if I solve this, this will be 1 into 1 minus 1 into 3 divided by 1. So minus 2 actually. And this will be 0 because here I have 0 only, no, does not matter. Now this will be basically, so if I have 0 here, directly I can copy this element. You can calculate, but you don't need to, right? So how many sign changes I have? So this is positive, this is positive, this is negative. First column is negative, positive. So no sign change, one sign change from positive to negative. Again another sign change from negative to positive. So total I have 2 sign changes. If I have 2 sign changes, that basically means I will have 2 poles on the right hand side of j omega axis. Okay, I will have 2 poles. I don't know the location of poles, but I will have 2 poles, right? So this will not be a Hurwitz polynomial. This will not be a stable system. Okay, for this also you can calculate, like these are just unknown values. Now from this, right, there is a very good trick for third order system. What is the trick? It is the concept of internal product and external product. So that will be like talk to you later as well. But if I see here, right, what is internal product? Internal product is basically the product between the coefficients of the internal terms. So if I find out the product of the coefficient of the internal terms, that is 1 cross 3, right? So internal product is 3. What about external product? It is 1 cross 1, right? The coefficients of products of the outside terms, it is 1 cross 1. Okay. So yeah, that's it basically. Now what do we need to do? So yeah, now if internal product is greater than external product, then system will be stable. So you see here internal product was 3, external product was 1, so system was stable. Here what is internal product? 1. What is external product? 3. So if internal product is less than external product, system will be unstable. Now, and there is one more condition: if internal product is equals to external product, then system will be marginally stable. We'll come to that condition as well, don't worry. But don't worry, like, this is not rocket science, this comes from this only actually. So what happens basically, this term, right? So if I derive it for the, yeah, this term, okay, for a general term, you will see here, right, what we are seeing. Okay, this is for the second, okay, this was for the second order equation. For third order equation, maybe I have solved somewhere. I should be able to, where is it, just give me 1 second. I must have solved for third order words. It's like a lot of things are there, don't worry, we will come to everything. Yeah, here. So if we solve right here for third order system, you will see that this term basically needs to be positive. If a0, a1, a3 all are positive, this term also needs to be positive. So if I make this term to be positive, so this is the internal product, this is the external product, that's all. So it's not like rocket science, I'm telling you something out of the world. No, it's coming from the route table only. Just there is a shortcut to not make the route table. We can skip making the route table and directly move on to our checking the stability. That is the important part, right? So for third order system, you don't even have to draw the route table. So if you enjoyed this trick, hit a like, put a comment down below that you have understood internal product and external product concept. Now obviously there are a lot of things we have to discuss, as you can see, so we will come to each and everything. So this has been discussed now. Okay, so Routh, I have told you how to form the table, all those things I have told you. Now there are few things, right? One more thing is there: if my characteristics equation consists only of even power of s, then that represents the presence of pole on the imaginary axis. Let us take a few examples. Let's say s square plus 2 equal to 0. The poles are at imaginary axis plus minus j root 2. Okay. Let's say s raised to power 4 plus s square plus 2 equals to 0. So let me solve this actually. Let me do it like this: 2s plus 1. Right. So if I assume my x to be s square, right, so this will be converted into x plus 1 whole square equal to 0. So x equals to minus 1, correct? So here I see s is basically under root of x, so s will be again plus minus j. You put here j, right, you put here j, this equation will be satisfied. You put here minus j, this equation will be satisfied. I will have 4 roots actually. I will have 4 roots. So one of the root will be plus minus j, and they will be repeated basically, plus minus j. So basically whenever your characteristics equation consists of only even powers, the roots will be basically uh, lying on the imaginary axis. They will be imaginary. Okay, that is one conclusion that we can take it from here. If my characteristics equation has its constant term equal to 0, then I will have root at the origin. Okay, this you don't need to remember. Okay, this you don't need to remember, don't worry about this. Okay, yeah. And also, let's say we have this exponential, right, we have this equation like e raised to the power minus st plus 1 equal to 0. How will I solve this if I want to calculate the roots here? So although this is not the proper method to solve it, but if you have to, right, in gate they will not ask you this, but in somewhere else if they ask you, what you will do, you will do the linear approximation. You will assume st to be very small, like almost equals to 1, so you can do the linear approximation that e raised to the power minus st would be 1 minus st. Okay, this will be the linear approximation, that's all. Okay, yeah, that's it basically. So yep, okay, we discuss about the we discuss how many. So from the route table, what can I conclude? I can conclude how many right hand poles are there. Okay, so this is a third order equation. This is a third order equation, and I have concluded that I have two right hand poles on the j omega axis. So I know for a third order equation I will have three solutions, three poles. Correct? Now what about the other pole? Now listen to me very carefully. If all the coefficients of my polynomial in S are real, then I will, if my poles are complex, then they have to be in complex conjugate format. This is a rule. Okay, this has to follow. How can you verify this? So simple, right? If I say s square plus 3s plus 1, right? B square minus 4ac. So okay, b square minus 4ac. Yeah. S square plus s plus 1. So you will see that you are always getting complex root, but always they are in conjugate pair. You will never see poles that are not in conjugate. Conjugate pair meaning, I hope you know what is conjugate pair. If one of the pole is lying here, other one will be exactly mirror image above the sigma axis, right? Sigma axis. So you will always get it in conjugate pair. So that is the thing over here, right? Now now what you will do is you will yeah, so here, right, if I'm able to see that I have two right hand poles and only I can have one more pole, and I know if I have complex poles, that means they have to be in pairs, so I can have two complex conjugate pairs, but only I have one pole that I can give, right? So this has to be a left hand pole. So that is how you conclude. So that is what I have written here. So imaginary poles always, they either s equal to 0 can be a pole that is at the origin, otherwise or I can have a conjugate imaginary pole, right? Now if I have a conjugate imaginary pole, okay, this, okay, sorry, I told you not to remember this, you can remember, right? So if my characteristics equation has its constant term equal to 0, so basically the constant term meaning this term, the coefficient of s raised to power 0 term, if it is 0, then I will have a pole at the origin, 100%, 101% I will have a pole at the origin, right? What do I mean? So let's say s square plus s equal to 0, the constant term is 0, so I have a pole at the origin. S cube plus 3s plus, that's all, equal to 0, so I have again a pole at the origin. So this is another important conclusion, right? So here, right, as I can see that the constant term is not 0, so I cannot have a pole at the origin, that is gone. I cannot have complex conjugate pairs of roots, that is also gone. So what is left? Only the option that is left is one pole on the left hand side, right? So I can conclude directly that there will be one pole on the left hand side. So that is what is written over here, one pole on the left hand side of the real axis. So how they can ask you the questions? So Routh table only gives us information about the number of poles on the right hand side, but in the question they will ask you how many poles are on the left hand side. So that you have to deduce from the Routh table. First you conclude that I have two poles on the right hand side and I can have three poles, right? Third order equation, three poles. So I cannot have a pole at the origin, I cannot have complex conjugate poles, because if I cannot have a single complex pole, because conjugate, like complex poles will always come in pairs, complex conjugate format. So only I can have a single pole on the negative real axis. It has to be a pole on the negative real axis. It cannot be a pole on the somewhere else other than the negative real axis, because if I have a pole here, then I must have another pole here. It has to be mirror image. If the coefficients are all real, if all these coefficients are real, then it has to follow. So only conclusion is I will have exactly a pole on the negative real axis. That is what I have written here. Okay, so these things are very important. They can ask questions from these particular thing, right? So yeah, these things they will ask question from this only, so please understand it. Now there are few special cases. So sometimes what happens is while solving, this element on the first column comes out to be 0. So whenever it comes out to be 0, how to solve that case, we will solve it now. So yeah, we have to find out the Routh table and check stability. So here, right, this is a large equation, okay, fifth order equation. So the table will also be pretty big. So let me solve the table. This will be 1, 2, so 1, 2, then 3, that's all. 1, 2, 3. This will be 1, 2, then 15. If I solve this, this will be 2 minus 2, that is 0. So I get a 0 here, right? If I get a 0 here, you will not write it 0. You will write it 0 plus a small value epsilon. So this actually is epsilon only. So epsilon is a, like epsilon is tending to 0 plus. It is a small positive number. That is our assumption. So now, so basically this sign should be same as whatever was the previous row sign, right? It should be same. Now what will be this this value? So this will be, so this will be right. Now okay, I have not yet told you how can you calculate the this element, right? This we have not come. So we know how to compute this particular column, but how to compute this one? So for this column, right, you will not actually choose this one. No, you will choose this. So you have to multiply this with this column and subtract this with this. Okay. So yeah, I have not told you. So now I am telling you for higher order how can you solve it. So 1 into 3, that is 3 minus 15, that is minus 12 upon 1, that is minus 12 only. And of course I have 0 here, so it won't matter. It won't matter. This will be 0 only. Now here, how will I solve? So this is epsilon. So this will be 2 into epsilon plus 12 upon epsilon. So 2 epsilon plus 12 upon epsilon. And because I have a 0 here, I can directly copy and paste this. Or you can do, this is epsilon into 15 minus 0 upon epsilon. So I can directly copy and paste. This will be 15 only, right? Directly this will be copied and paste. This is 0 again. So now this will be a bit difficult. So bear with me. So this will be 12 into minus 12 into epsilon. Okay, how will I solve this? This is also epsilon, right? This will be a bit difficult. Okay. Limit as this is tending to 0. So what we can do is, like, although like I will show you the basic method, then we can discuss about the other methods. So this, right, will be equals to like this term will be equals to, here I will multiply these two and then subtract these two, correct? So this will be 2 epsilon, or let me divide by epsilon first. Yeah, let me divide by epsilon. If I divide by epsilon here, right, this will be 2 plus 12 by epsilon, that's it. Okay, great. Okay. So okay, if I multiply these two, 2 plus 12 by epsilon into minus 12 minus 15 epsilon, this divided by this value, right, this value, which is very difficult. Okay, yeah, okay. So okay, it's better, like what I can assume is this. Let me assume this to be x, right? So this is x minus 12x minus 15 epsilon upon x only, right? So this will be minus 12 minus 15 epsilon by x. Now the thing is that this x, right, it is tending to plus positive infinity, correct? X is tending to positive infinity, because if I put here epsilon equal to 0, this will be 12 by 0, which is 0 is some positive number, right? 0 plus, so this is tending to positive infinity. That is I know. So actually this term will be simply 0, because epsilon itself is 0 plus upon positive infinity, that is 0. So actually this value comes out to be minus 12 only. So you can actually simplify this. Okay, you can simplify this. That is a trick basically. And of course, if I have a 0 here, right, simply I will copy this element over here. So this will be 0 only. Now it is much easier. If I have a 0 here, I will copy this element over here, that is 15, and after this everything is 0. So this also will be 0 0, correct? Now how many sign changes are there? So this is minus 12. So what is this? This is plus 0 plus, right? So this is some positive value. Again this is going to positive infinity, so this is also positive. So this is plus 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 minus plus. So I have two sign changes, correct? Not two, sorry, yeah, I have, yeah, two sign changes. If I have two sign changes, that means there will be two poles on the right hand side. There will be two poles on the right hand side, that's it. Okay, I have two sign changes, that means there will be two poles on the right hand side. So system will not be stable. So let us use for this one as well, right? This is the classic example, right? Anyways, I can directly see that internal product is equal to external product, so system will be marginally stable. How it will be marginally stable, we will see that. So here if I see, if I write this s cube s square 0, this will be 1 1 1 1, this will be 0. If this is 0, this will be 0 plus epsilon, and this is anyway 0. Okay, so if this is 0, this will 1 will come here. So automatically I say that uh, this is some positive value. Okay, but okay, now there is a conclusion here. So this is 0, right, and the next row is also 0. So if I get a row of 0, then we have another special case. Okay, although you will say that there is no sign change here, partly you are correct, but I am getting a row of 0, right? So row of 0, there is a special condition. Okay, here the row was not totally 0, right? If row is not totally 0, you will solve like this. If I am getting a row of 0, then you have to take a pause. If I am getting a row of 0, right, that means you have complex roots on the imaginary axis. Okay, how? So the roots, how will you calculate the roots? So you will take the previous equation, that is called as the auxiliary equation. The row above the row of 0, this is called as ROZ, row of 0, is called as the auxiliary equation. The row above the row of 0 is called as the auxiliary equation. Okay, so this, right, how will I form the auxiliary equation? So with s square I will put its coefficient, that is 1, and then of course this is the first coefficient, right? Then we obviously, if you remember, we ignore the next power term, we directly take the term after that. So this will be coefficient of s raised to power 0. So 1 into s raised to power 0, this I will equate, this is my auxiliary equation, right, a of s. This I will equate to 0, and this will give me two poles of my characteristics equation. That is the beauty. Okay, that is the beauty basically. So here I will get s square plus 1 equal to 0. So s is equals to plus minus j, and this will be one of the roots of my equation. If you put here plus minus j, these two are roots, correct? So that is the beauty. That is the beauty of Routh-Hurwitz criterion. You can actually calculate exact location of roots as well. Now we got two roots that are lying on the imaginary axis, correct? And other than that, there is no sign change. If there is no sign change, the other root also will be lying on the left hand side. So I will have two roots on the j omega axis, and I will have one root on the negative real axis, because there is no sign change, right? Other than that, the sign is always positive. So I hope that part is clear by you. Okay. So yeah, that's how you solve basically. Now, how will you find the location? How will you find the exact location of the root, right? Let's say I want to find the exact location of the root because I have only one root left. So you can use long division method, right? So we know s equals to plus minus j is a root. So basically s square plus 1 is a factor of my equation. So s square plus 1 into a particular polynomial, let's say c of s, will be equals to this polynomial p of s, correct? Because s square plus 1 is a root, correct? S square plus 1 is a root of my equation. So I can break this into factors. This is taught to you in class 8-9. So I can break this into factors. So basically I can actually, if I am able to find out c of s, right, I can comment, because this will be a first order equation, because this is a third order equation, I can comment about the location, exact location of the left hand side pole. So what I can do is I can divide c of s will be p of s upon s square plus 1. So I can take help of long division rule. So I have to, what is p of s? S cube plus s square plus s plus 1. What is your polynomial auxiliary equation? S square plus 1. So I will use long division method. So how to use long division method? Basically your first target should be to eliminate the highest order term. So here with s cube I have 1. So I will multiply this with something so that I can eliminate this. So if I multiply by s, right, so this if I multiply this with s, right, this will be s cube plus s. So I will put everything in order, and of course we are using long division, so just search how to do long division. Okay, you will get the idea. So this will be 0, this is gone, s cube is gone. Now what is left? S square plus 1, right? S is also gone. So again if I multiply plus 1 here, this also will be gone basically, right? 0. So my factor is s plus 1. So I have another root at s equal to minus 1. That is the beauty. So if we put here s equal to minus 1, you will see it is satisfying, right? So that is the beauty of Routh-Hurwitz. You can actually sometimes, you are lucky, if you are lucky, you can exactly find the location of roots as well, if you are lucky. Because I was getting row of 0, so the row above the row of 0 is called as the auxiliary equation. If I make the auxiliary equation to be 0, I can compute the conjugate roots, location of my roots, imaginary roots, and with that also I can find out the location of the other root as well. And whatever we concluded, right, I told you that we will have exactly one negative real root from this first row, because there is no sign change. So there is no roots on the right hand side. There are no roots on the right hand side. So two roots are gone. So one root can be only in the negative real axis, and that is what we have exactly computed. One root is on the negative real axis at s equal to minus 1. S equal to minus 1, the root is at the negative real axis. That's all. So yeah, now these are few things like roots will be real when row of 0 is there, like radially opposite. These things you can understand by the statement type questions. I am not going into this because how many things will you remember, but that's fine. Like what do I mean? So radially opposite meaning that roots will be absolutely symmetric about the origin. Okay, so if I have a row of 0, right, if I have a row of 0, then roots will be radially opposite. Basically roots will be symmetrical about the origin. So either you can get a complex conjugate root, or that is exactly lying on the imaginary axis, or if the roots are not lying on the imaginary axis, they will lie exactly on the real axis. Either they will lie on the j omega axis, or they will lie on the real axis, sigma axis. They will not lie anywhere else. Okay, they can lie anywhere else as well. So basically your roots can be like this as well, right? Yeah. So basically, right, whenever you're getting a row of 0, you will get roots that will be radially opposite. Radially opposite meaning roots will be symmetrical about the origin. They can lie here. Also, if it's a fourth order auxiliary equation, then roots can be like this as well, right? That is also another possibility. So mostly you will get second order equation. And if you are getting second order equation, right, if you are getting second order auxiliary equation, that means your roots can either lie on the j omega axis or sigma axis, because if I have two roots, right, so this is not a proper radially opposite setup, but actually sorry, okay, still they can lie here. So this is also a proper radially opposite. So these two roots are radially opposite to each other, right, symmetric about the origin. Okay, they are symmetrical about the origin. So yeah, these two roots are also symmetrical about the origin. Yeah, so we cannot conclude anything. So just the only conclusion is, if I am getting a row of 0, then 101% my roots will be radially opposite. What do I mean by radially opposite? That roots will be symmetrical about the origin. That's all. Okay, that's all. Now yeah, let's do few row of 0 calculations, and with that we will understand. So this is the first one actually. Let's do this. Okay, bit big calculations, but that's fine, we can do it. So you pause the video and try it out by yourself. Let's solve this basically. So let me first of all form the Routh table. So here I will write here s raised to power 6, s raised to power 5, s raised to power 4, s cube, s square, s raised to power 1, s raised to power 0. Now this will be 1, then I will write 6, then I will write 12, then I will write 8. Okay, big table. Okay, big table. First here will be 3, then I'll write 12, then I'll write 12 again, and then of course after that nothing is there, so it's 0. Now let me first of all compute the first table. So it is 3 into 6 minus 12, so it is 18 minus 12, 6 upon 3, that is 2. So safe, I am safe, we will not get a row of 0, or I don't have to consider epsilon in this case, because whenever the first element is not 0, then you are safe. Now the next element, this would be 3 into 12 minus 12, that is 36 minus 12, 24 by 3. 24 by 3 would be 8. Okay, next this will be 3 into 8. So 0, I have 0, right? I can directly copy this. I will directly copy this and paste it over here. So this will be simply 8, that's all. Now next row, so this will be 2 into 12, 24 minus 24. So I am getting a row, I am getting a 0, but I don't know yet whether this will be a row of 0 or just a single element being 0, first element being 0. Let me compute the other elements as well. So if I compute this, 2 into 12, 24 minus 24 again, so this is also 0, and this is also 0, right, because this element is 0. So if this element is 0, I will just copy this element, that is 0 only. So I'm getting a row of 0, that's all. So if I'm getting a row of 0, then what will I do? Okay, one more thing I forgot to tell you, sorry, here, right, okay, so one more thing I forgot to tell you, unfortunately, here. Okay, one more key point was there, right? Whenever I get a row of 0 here, this I forgot to tell you at that time. At that point of time, I forgot to tell you that whenever I get a row of 0, right, then you will replace, like, first of all, you compute the solution of auxiliary equation will be the location of my poles, will be one of the solutions. Now what will you cannot put 0 here, right? If I put 0 here, then you cannot actually compute the next element. Although I computed using epsilon, because I had a 0 here, I simply copied here, it did not matter in this particular case. But actually this, right, this will be changed actually. This row of 0 will be changed. Okay. Now what will be this row? This row will be just the, my auxiliary equation is what? Auxiliary equation is s square plus 1. This is my auxiliary equation, correct? So if I differentiate my auxiliary equation with respect to s, this will be 2s. So the coefficient of s, right, will come here then. That's all. So the row of 0, this will be 2s plus what, after this I have 0, right? Does not matter. So actually we will replace your row of 0 with 2 and 0. That's all. We were very lucky because this was coming out to be 0 as well. So we got here 1. So this is another thing that you have to keep in mind. So that thing we will do here. So you will understand it better. So here I got a row of 0. So if I got a row of 0, first of all, your first task would be to like you can do it, but it's up to you if you want to do it or not. But it's good to know that you can calculate the location of roots. So let's say that we don't care about the location of roots. What I care is what will be this value, because if I have row of 0, right, you cannot continue, you have to pause and replace your row of 0 with this equation. So my auxiliary equation is this 2 into s raised to power 4 plus 8 into s square plus 8. So now if I differentiate this, right, if I differentiate this, this will be dA of s upon ds, this will be 8 s cube plus 16s. So the coefficients, right, coefficient of s cube is 8. So in s cube I will have 8 here, right, this 0 will be replaced by 8, and this 0 also, like what is the coefficient here? This is the coefficient of s cube, this is the coefficient of s raised to power 1, because I reduce by power of 2. So what is the coefficient of s raised to power 1? 16. So I will write here 16. Now what will come here? Nothing, right, because it will be coefficient of s raised to power minus 1. We don't consider negative powers, so it will be 0. So we are safe. So we will replace it. We will replace the zeros to here. Of course, we can compute the location of the roots as well for this row of 0. Location of roots will be this equation. Okay. So I will solve this equation. Solution of this equation. I will solve this. Don't worry. But for now, let us continue with the Routh table. So this became 8, 16. Now if I solve it again, right, this will be 8 into 8, that is 64, minus 32. 64 minus 32, that is 32 upon 8. 32 upon 8 is 4. And here I have 0, right, so I can directly copy this. So yeah, now I don't get a row of 0, so no problems. So this will be 4 into 16. 4 into 16 actually is 64, and 8 into 8 is also 64. Again I am getting a row of 0. Again I got a 0. Let us check for the other elements as well. The other element, this also will be copied. Will this be? Yeah, this also will be copied because I have a 0 here, right? This also will be 0. So this is a problem. Again I am getting a row of 0. So again I have to cancel these things. So again another equation I will form. So this will be auxiliary equation 1, auxiliary equation 2. So this will be equals to the previous row. So 4s square plus 8 raised to power 0 equals to 0. So equals to my auxiliary equation. So the solutions of my auxiliary equation will give me again location of poles. Okay, and these poles and these poles can be same. We will verify that, but these can be same. Now what will be this row, this last row? So this will be, if I differentiate this, this will be equals to 8s. That's all, right? If I differentiate this with respect to s, this will be 8s. So the coefficient of s raised to power 1 will be 8. This will be, and this is anyway 0, does not matter. So ultimately here you will get 8. Now how many sign changes are there? There are no sign changes. So there are no poles on right hand side, right hand plane or right hand side of j omega axis. So there are no right hand side poles, 100% sure. Okay, there are no poles on the right hand side, that is I'm 100% sure. Now what about the location of poles? Can I compute the location of poles? Yes. So here, right, if I find the solution of this, this will be s square equals to 2. So I have 2 poles at s equals to plus minus j under root 2. So 2 poles I got at s equals to plus minus j under root 2. What about this pole, right? What about the location of poles here? So if I solve this equation, correct, this will be s raised to power 4 plus 4 square plus 4 equal to 0. So if I assume my x to be s square, this will be x plus 2 whole square equal to 0. So x is equals to minus 2 comma minus 2. Okay, so the poles, right, s will be like plus minus j root 2 and plus minus j root 2. So already, right, whatever poles I will get here, right, these will be whatever poles I will get in this equation, right, in this equation, sorry, whatever poles I will get in this equation, this, right, already will be included here actually. So the first ROZ will already provide me this poles, already it has provided me, right. Now the thing is, the number of ROZ tells me how many poles will I have repeated. How many total row of 0 I have? 2. So how many poles are repeated? 2 poles are repeated, right. So plus j root 2, it is repeated twice. If you see here once and here once. Minus j root 2 also is repeated twice. So the number of ROZ gives me the information about how many times my pole will be repeated. That is what it is written over here. Okay, number of ROZ gives me the information about how many times the poles will be repeated. Okay, now do we need to remember it? It's up to you, but of course they will give you the poles and those things, right? They will give you the characteristics equation. You can solve. I also forget it. I will forget this property, but I will solve the equation, and from that I will figure out something. Okay, that's up to you. Yeah, so I got 4 solutions, and this is a 6th order equation. So the other 2 roots will be either complex conjugate or they will be lying on the real axis, but they will be on the left hand side of the j omega axis because there is no sign change. So this system will be, I cannot comment about stability because I have poles on the j omega axis, but of course I can say that there are no poles on the right hand side. That is the conclusion. So that is how you can solve using row of 0. Of course, now can you find out the location of poles? If you want to verify, again you can take help of the long division method, because you know this, right, your auxiliary equation is a factor, correct? Your auxiliary equation, because if I make this 0, it will satisfy the roots. So auxiliary equation actually is a factor of my main equation. So I can divide by auxiliary equation with the main equation, and if I divide, I will get this solution, right, this quotient. And if I find out the solution of this quotient, like that is what I have done here, I guess. If I find out the solution, you are seeing that you are getting 2 roots on the negative real axis. They could have been complex conjugate as well, but we got 2 roots on the negative real axis. So I have proven it to you as well that there are no poles on the right hand side. I have proven it to you. Right? From the table, we concluded that there are no poles on the right hand side, but from this proof, right, directly showing you that s equal to minus 2, s equal to minus 1 will be 2 poles that are lying on the left hand side. So there are no poles on the right hand side. So I have proven it to you by calculating the location of roots that Routh table actually works. So if you have finally enjoyed Routh table, hit a like and drop a comment. So we have to do marketing in between so that this session is interactive, right? So yeah, that's all. So again, you can solve for this. I will not solve for this. You can solve for this. You will get some equation, like either you can find out the solution of this. This will be difficult for you to solve. You can solve, like here, right, one interesting thing will happen, that your auxiliary equation, this will be 6s raised to power 4 plus 24. How will you solve this? So this I have taught you that we can write minus 1 to be e raised to power j pi in complex numbers. I have taught you. So we will replace that, and then we will find there will be 4 solutions, and this will be my 4 solutions basically, right? There will be 4 solutions. So yeah, actually there will be 4 solutions. So here, right, this can be basically, if I am dividing by 4, so this will be, right, e raised to power j pi plus 2n pi, correct? So basically for n equals to 0, this will be e raised to power j pi. So for n equals to 0, this will be one of the solution. There are 4 roots. Remember, there are 4 roots. The other root will be for n equals to 1. For n equals to 1, this will be 3 pi, right? If this is 3 pi, I will divide by 4. So another solution would be e raised to power j 3 pi by 4. Okay, and then another solution will be, if I put n equals to 2, if I put n equals to 2, this will be e raised to power 5 pi. So this will be 5 pi divided by 4, and the final solution will be, if I put n equals to 3, if I put n equals to 3, this will be e raised to power 7 pi. So the other solution will be e raised to power j 7 pi by 4. This I have already taught to you how to find out the solutions in complex numbers of complex complex numbers only. So I hope there is no confusion here. Okay, so that's how you basically solve these kind of equations. I will not go through too much in detail, already we have discussed few things, right? Okay, so rho of 0 represents either my system will be marginally stable or unstable, because I am having poles on the, because I can have poles on the imaginary axis. So that means either I will have marginally stable system or it can be unstable, because this is also a solution of rho of 0, right? This is also a possible solution. So if I have rho of 0, then certainly you can say your system will not be stable. If you are getting rho of 0, certainly you can say your system will not be absolutely stable. Either it can be marginally stable, because you can have poles on the j omega axis, or it can be unstable. These are the two possible cases. There is no case for stability. It will not be absolutely stable. Okay. Rho of 0 will only occur in odd power. You will observe that rho of 0 only occurs in odd power of s. It will never occur in even power of s. You will observe this, right? And obviously even auxiliary equation will only consist of even powers of s. Okay, it will only consist of even, whatever auxiliary equation you have derived, right? Here if you see auxiliary equation, it had only even power of s. Here also if you see auxiliary equation, it had only even power. This is s raised to power 0, that is also even power. So you will only get even power of s, that's it. Okay, so yeah, these are few conclusions regarding rho 0. I have already discussed about this condition. This has been discussed, internal product, external product. Yeah, for this what you will do is compute the route table for the system to be stable if OLTF is this. If OLTF is this, again you have to compute the route table. So what you will do, you will replace e raised to power minus st by 1 minus s tau, and you will, this is my OLTF, right? You will compute the CLTF, and then you can compute the route table. Okay, so basically they are asking you what is the condition on t. This should have told you what is the condition of t. If you solve this, right, basically all the, for second order equation, simply all the coefficients must be of same sign. So if all of them must be of same sign, this is positive, this is positive, so this must also be positive. So 2 minus t by 2 must be positive. So from there you get the condition t less than 4. Or you can compute the route table, you will get the, so not here, you can compute the route table and you will get the same answer. Okay, so these are few basic conditions. Okay, so this you can solve. Like I hope I don't need to solve it. Like the system is described by the transfer function, the constraints on alpha and k for the system to be stable. You can simply, this is a third order equation, right? So I can take help of internal product into external product. Internal product must be greater than external product. Internal must be greater than external. So your internal energy must be greater, right? How can I remember? Your internal energy must be greater than external. Basically, whatever energy you have inside, it will come outside, it will reduce due to some noise or something, right? So that's how you can remember that internal product must be greater than external product for stability. For stability, for marginally stable, they can be equal. So alpha into k must be greater than 3. So condition is, yeah, that is the condition, alpha into k must be greater than 3, or you can solve using the route table, you will get the same condition. Yeah, so now let's come to the next topic, that is regarding frequency of oscillations. So we know what is frequency of oscillation. I hope you remember that if I have a frequency of oscillation, that means the response will oscillate with that frequency. There can be damping as well, but it will oscillate. So if I have some frequency of oscillation, that means, right, if they're asking me the oscillation frequency, or sometimes it is also called as a natural oscillation frequency, right? That means when it is oscillating naturally, when there is no damping present, that means I will have the poles on the j omega axis, correct? So if I have poles on the j omega axis, then what I can do, I can compute the route table for this. I can compute the route table for this. Then I can find out the roots of the auxiliary equation, and that will provide me the natural frequency of oscillation. That is bit lengthy actually. So whenever your equation, right, is fifth order or lower, so you don't need to do this. you can use a bit of trick, because you already know they're asking you oscillation frequency. That means if I put s equal to j omega, it has to pass through, like it needs to have poles at s equal to j omega. Otherwise, why will they ask me oscillation frequency? It has to have that, right? If it does not have, then like I will also tell you whether it will cross the j omega axis or not. How can you verify that? That also I will tell you. Okay. For now, just understand this thing, that if I put j equal to s equal to j omega, I will be able to calculate natural frequency of oscillation. Correct? So how will I do it? So what we can do is, I will put s equal to j omega. If I put s equal to, of course, I will solve it using the Routh as well. I will tell you that as well. So if I put s equal to j omega, this will be j omega raised to the power of 5 plus 4 into j omega raised to the power of 4 plus 6 j omega raised to the power of 3. Okay, hold on a second. Just give me 1 second. I might have missed something. This would also be, I think this will be, okay, I missed few terms. Yeah, so I have created the polynomial. So finally we're done. So there was a problem of 2, that's it. So yeah, now let's solve it. Let me put s equal to j omega. So this will be j omega raised to the power of 5 plus 4 j omega raised to the power of 4 plus 6 j omega raised to the power of 3 plus 6 j omega square plus 5 j omega plus 2 equals to 0. Correct? Now, of course, we will equate the real and imaginary part. Imaginary part must be 0, real part must be 0. So, if I solve this, right, if I solve this, yeah, this will be basically my, so I will only take the real terms, okay, or you can take the imaginary terms, but I'm not comfortable with solving like power 4, power 5, right? I am comfortable with power 4. Why? Because I will assume my x to be omega square. That's why I'm comfortable. So this will be actually plus omega raised to the power 4 minus 6 omega square and plus 2. That's all. So if I divide by 4 and if I assume x to be omega square, this will be x square minus 3 by 2 x plus 1 by 2 equal to 0. So this will be b square minus 4ac. So this will be minus b plus minus b square 9 by 4 minus 4ac. 4ac would be 2, yep, upon 2a. So this would be 3 by 2 plus minus, this is 1 by 4, that is 1 by 2 upon 2. So this will be 2 or 1, right? So 1 or plus minus, if I add this, this will be 2 upon 2, that is 1. If I subtract, this will be 1 upon 2, that is half. So either it is 1 or half, correct? So either my x, so x is 1 or half, so omega would be either 1 or 1 by root 2. Okay, actually we should get a negative solution as well. That is what I'm thinking. Minus b plus minus b square minus 4ac. So from 3 by 2, 4, 2 by 2, 1. This is 2 by 2, that is 1 only. 1 by 2, huh? Okay, so we are getting two solutions. Now which one is valid? So to verify that, right, actually you have to solve the this imaginary part as well. So imaginary part tells me that the imaginary part must also be 0. So here this is what? This is nothing but minus of omega raised to power 5. So minus of omega raised to power 5 plus of, this will be, sorry, this will also be minus, correct? Sorry, this will be plus of, so this will be plus j omega raised to power 5. I hope we can do all this. Minus j of omega 6 into omega cube and plus j is there, right? Plus j 5 omega, this has to be equals to 0. This has to satisfy, basically this has to be satisfied, correct? So if this is satisfied, if I put omega equals to 1 here in this equation, this will be j minus 6j plus 5j, which is satisfying. So this is fine. If I put omega equals to 1 by root 2, this will not satisfy here. Okay, this will be j divided by, now this is 2 raised to power 5 by 2 minus, this will be something weird, right? J divided by 2 raised to power 3 by 2 plus 5 by plus 5j divided by root 2, 2 raised to power half, which is something where this will not satisfy, this will not be equal to 0. So definitely this will be your valid solution. So omega equals to 1 is a valid frequency of oscillation. Now you might ask, sir, what if there is no frequency of oscillation? What if it does not cross over, right? There is no intersection in the j omega axis. Then in that case, what will happen? The solutions that we will get here, right? The solution that we will get here will be invalid. Basically, you will get a solution like omega equals to, so basically your solution of x, right, will be negative. If your solution of x is negative, that means your omega will be imaginary, and if it is imaginary, that is not possible. Already I have considered the imaginary part, right? Omega is a real number. Already I have multiplied by the imaginary term. So omega has to be real. The valid domain of omega is from 0 to infinity. So omega must lie in this domain. If it is lying outside, that means something is wrong. That means there is no frequency of oscillation. Got it? Omega must be real. Basically, omega, the solution that you will get here, right? Omega must be real number, real positive number. It must be a real positive number. If it is not a real positive number, that means there is no frequency of oscillation. Now, how can I verify? You can again use the Routh table. So let's do it actually. Use the Routh table. If I use the Routh table for this equation, so first of all, let me write here. It at first glance, it seems very like big solution, big method. You might feel that Routh is easier, but not always. Sometimes Routh will be easier, sometimes this will be easier. So it's better that you know both the methods. So this will be 1 1 4, so not 1 4, sorry, 1 6 1 6 1 6, just give me 1 second, 1 6 5 1 6 5, yep. Then I have 4 6 2 4 6 2. So if I solve this, right, this will be 4 into 6 minus 6. This will be 24 minus 6. So 18 divided by 4. So 18 divided by 4 is 4.5. 4.5, right? 18 divided by 4 is 4.5. This will be 20 minus 2, that is again 18 divided by 5, that is 4, also 4.5. Okay, interesting. This is 0. Am I doing this correctly? Let me just check. 165 165 462 462, that is correct. If I solve this, this is 24 minus 6 divided by 4, 18. Okay, this is 20 minus 2 divided by 4, that is again 18. 18 divided by 4, yeah, is 4.5. Okay, so this will be what? This, if I calculate 6 into, so this will be basically 6 minus 4, that's all. So this is 2. Okay, and this will be basically, this is 0, so I can copy this column. This is also 2. Now this will, I will get a row of 0 here, right? I get a row of 0 here. If I get a row of 0, then this will be my auxiliary equation. So my auxiliary equation would be s square 2s square plus 2 equal to this. So this is my auxiliary equation. So the solution of this will be s square plus 1 equal to 0. So s will be equals to plus minus j. So it seems very easy. Okay, this Routh, in this case it was very simple. Okay, but sometimes that method also will be very simple. Okay, it might seem, okay, this method was more complicated than this one. That was not the purpose, but luckily Routh was the simpler one. But like, you have to be smart enough to use what method. Okay, you have to be smart enough to use, like, when to use what method. You have to understand that. Okay, so if this is a row of 0, I got the frequency of oscillation, that is done. But of course, if I want to solve this, right, I will get, this will be 4s equals to my d of s, that is a differentiation. So here I will have 4 and 0, so this 2 will be copied. So all the other roots will be on the left hand side. There will be no roots on the right hand side, because all the first column, all the rows are positive in the first column. So that's why. Okay, so let's solve another question. So these kind of questions also sometimes is asked regarding the condition of k. The condition of k such that the roots of the characteristics equation lie on the left of the line s equal to 1. Now they are not asking that so whatever we have studied till now, we have studied for the condition that either they are on the left hand side of the j omega axis. So what is this? This is simply s equal to 0 line, right? S equal to 0 line. Okay, that is the condition that we have learned. If they are on the right hand side, then of course I will plot the Routh table, and from there I can solve and I can check the number of sign changes. But they are asking me which of the following poles will lie on the left half of s equals to 1 plane. How will I solve it? So what do I need to do is, because whatever we have been studying till now was with respect to s equal to 0 line, right? S equal to 0. When the real part is 0, omega is varying. Omega is varying from positive infinity to negative infinity. Correct? So we have been solving for this case. So what I can do, I can convert my equation into this plane. So what I will do, because I have told you Routh is valid for any kind of polynomial, not only for characteristics equation. So I will convert from s plane to z plane, because I am comfortable to compute the right hand poles from s equal to 0 line, right? So if I convert this to z plane, and if I say that s equal to 1 line in s plane will be z equals to 0 line, right? So if my s is equals to 1, then z is equal to 0. So what is, if I can convert this equation, this is s minus 1, that is equals to 0, and my z is equals to 0. So basically I can say s minus 1 is equals to z. So that is the substitution that I will make, because I am comfortable in understanding this. Either I can comment around z equal to 0 plane or s equal to 0 plane. Because they have asked me s equal to 1 line, I am not comfortable with that. So I will convert my equation into z plane, and I will comment regarding the z plane now. So let me solve it. So I will do this conversion. So s equals to, I have to compute about s equal to 1. So I can take this one on the other side. So s minus 1 will be 0, and the 0, right, is like s equal to 1 in the s plane is same as z equal to 0. So I can replace 0 to be z, right? So now my s will be substituted to z plus 1. Okay, you cannot simply solve it like you will use internal product greater than external product. So you will say that which lie on the left hand side, so you will say internal product greater than external product, because it has to be stable. So you will say 180 greater than k, right? So k has to be less than 180. That will be a condition. You are partly true, because whenever you are doing this, right, that means you are telling that if my k is less than 180, then all my poles will lie on the left hand side of s equal to j omega, or s equal to 0 line, basically, right? S equal to j omega. So this particular area, but they have asked me not only this, they have asked me to include this part as well, this region as well, s equal to 1. So we are not including the right hand side poles here. So I have to include this region. How can I do it? So what I will do, I will do a bit of transformation. So I will replace my s equal to 1 to z plane. So s equal to 1 will be replaced to z plane. So this line has been shifted on the left hand side. That's all. So now I will comment which poles are lying on the left hand side of z plane. Z equal to 0, and z equal to 0 is nothing but s equal to 1. Okay, got it? So yeah, so I will replace my s with z plus 1. So if I replace my s with z plus 1, this will be z plus 1 whole cube plus 10 into z plus 1 whole square plus 18 into z plus 1 plus k. This has to be equals to 0. So this will be a bit lengthy. So this will be z cube plus 3z square plus 3z plus 1 plus z square plus 2z plus 1 plus 18z plus 18 plus k. So if I solve this further, this is equals to 0. This will be z cube 3z square plus 10z square, that is 13z square, 3z plus 20z 23z plus 18, right? 23 plus 18, so 21 plus 20 41z plus this will be 1 plus 18 19 plus k. Okay, 19 plus k equals to 0. Now I can use the internal product, external product. This will comment about the z plane, right? And I'm concerned about which poles are lying on the left hand side of z equal to 0, right? So that is fine, because that is what I'm interested in, because z equal to 0 is nothing but s equals to 1. Z equal to 0 is nothing but s equals to 1. Okay, so yeah, if I put here, if I use the internal product formula, so it will be hold on a second. This is 10 plus 1 11 11 plus 18, sorry, this will be 9, this will be 29, this will be 29. Okay, so this is my constant term, this is the z raised to power 1, this is raised to power 2. So internal product is 13 into 41 must be greater than 1 into 29 plus k. So if I solve this particular thing, this will be 13 into 41 minus 29. So basically your k must be less than 504. So if your k is less than 504, that means all the poles of z equal to 0 are lying on the left hand side, and that means all the poles of s equals to 1 are lying on the left hand side of s equal to 1. So this concept is called as mapping. We don't need to understand the like basically this per se, right? Like exact words, but that is fine. Also, this is the upper limit of k, right? What is the lower limit of k? So we know for any third order equation, right? For it to be Hurwitz polynomial, all the coefficients must be positive, basically of the same sign, right? So if this is positive, this is positive, this is positive, this also has to be positive. So basically 29 plus k has to be positive, so k has to be greater than minus 29. So this is the lower limit of k and this is the upper limit of k. So k must lie within this range. Okay, so I hope you have understood this particular point, the concept of mapping. These are few symmetric conditions, no need to worry about this, these are not that important. Now we will start off with the gate PYQs. Okay, so let's start with this first question. So consider the open loop transfer function, the value of k for which the system is marginally stable. It is a OLTF, remember, this is not the CLTF. So they have mentioned negative feedback system, but they have not mentioned whether it is a unity negative feedback system or non-unity. So by default you will assume it to be unity negative feedback system. So if I assume it to be unity negative feedback system, so if I find out the CLTF, so for that first of all I have to compute the characteristics equation. So if I compute the characteristics equation, right, this will be basically 1 plus g of h into h of s equal to 0. This is my characteristic equation, right? Because your transfer function is g upon 1 plus gh and your characteristic equation is this denominator equal to 0. That is what I am doing. So if I make this, right, this will be s into s plus 2 into s plus 6 plus k s plus 11k equal to 0. So this will be s square plus 10s (16) plus ks plus 11k equal to 0, s cube plus 10s square plus this is 16s plus k, so this will be 16 plus ks plus this will be 11k, right? So we can easily find out the condition basically, right? First of all my coefficient must be positive, correct? All my coefficient, like you can solve using Routh table, right? That is up to you, that is the homework. All my coefficient must be positive, but they are asking what is the value of k for which the system is marginally stable. When my system is marginally stable, when my internal product is equals to external product. So 16 plus k into 10 must be equals to 1 into 11k, that's all. So this will be 160, this will be k, so k will be equals to 160, that's all. So 160 will be your answer for the question. Let's solve the next question. So next question is this one, where we have been given like which of the following options is correct. It is a like fourth order system, stable, unstable. So what is the order? So order would be the highest degree of the characteristics equation. So if I find out the characteristics equation, it is 1 plus g h equal to 0, correct? So 1 plus g, that is 20 upon s plus 1 into s square into s plus 20 equals to 0. Okay. So yep, now this will be basically, if I solve this, right? So I see that highest power is of 4, so it is a fourth order system, it is not a third order system, definitely, right? So let me solve it further. So this will be s square into s square plus 21 s plus 20 plus 20 equal to 0. So this will be s raised to power 4. Okay, that is interesting, we don't have any. Okay, it is not stable, right? I can directly say it is not stable. Why? I will explain. So plus 21 s cube plus 20 s square plus 20. Okay, what is the problem? This is not a Hurwitz polynomial because the necessary condition, not the sufficient, because it is a higher order equation. The necessary condition for it to be Hurwitz, all the coefficient must be non-zero and of same sign. But here I see I don't have any coefficient for s, it is 0. So it is definitely not a Hurwitz polynomial. If it is not a Hurwitz polynomial, simply the system will not be stable. Few poles will be lying on the right hand side. So it is an unstable system. Option C is correct. Your homework is to compute the Routh table for it. If you compute the Routh table, you will arrive at the same solution. Let's solve the next question. Consider a negative unity feedback system with the forward path transfer function to be this. Okay, this is the forward path transfer function. Okay, forward path. This is not the closed loop transfer function. Forward path meaning this will be g into h. Okay, where k is positive real number. The value of k for which the system have some of its poles on the imaginary axis. What shall be the value of k if some of its poles are on the imaginary axis? This is the third order equation, right? So what will be the characteristics equation? 1 plus gh equal to 0. This is my OLTF, right? That is what is given to me. So this will be basically 1 plus s square plus s plus 1 by s cube 2s square plus 2s plus k equals to 0. So I can directly say that s cube plus 2s square plus 2s plus k plus s square plus s plus 1 equal to 0. So this is a Hurwitz polynomial. So this will be 2 plus 1 s square, so 3s square, and this will be 3s, right, plus k plus 1. Now they are telling me that few poles must lie on the imaginary axis. When does my pole lie on the imaginary axis? When my system is marginally stable. So simply use this condition, internal product is equals to external product. So 9 is equals to k. So k, the value of k must be 9. That's all. Okay, so hold on a second. 3 into 3. So 9 equals to k plus 1, right? This is k plus 1. Constant term is k plus 1. Don't make this mistake because 9 is also in the option. Okay, I also would have ticked to 9. Okay, just be careful. Be very, very careful. This is k plus 1, right? So k is equals to 8. Be very careful. So option B is correct for this particular question. That's how simple it is. You can obviously compute the Routh table, but we will use bit of shortcut here. So let's solve the next one. The closed loop characteristics equation of the system is given by this, right? The frequency of oscillation. Now in this case, right, of course you can compute the Routh table. We will do it using both methods. Let's compute using our method that we discussed. Replace S with j omega. So if I replace S with j omega, this will be omega j omega raised to the power 4, right? That is simply omega raised to the power 4. This will be minus 2j omega cube minus 8 omega square plus 8 j omega plus 16 equals to 0. Okay, so yeah, now we have to equate the real and imaginary parts. So if I equate the imaginary part, right, equal to 0, so basically 2j omega. For fourth order equation it is much simpler, right? It is much. Fifth order equation bit difficult. So minus 2j, okay, yeah, you can either equate the real and imaginary. So I will first choose the imaginary part because here the power is lower, right? Whichever power is lower, I will choose that. So this is minus 2j cube plus 8 j omega equal to 0. So one solution is omega equal to 0, that is not a solution. Okay, omega equal to 0 is definitely not a solution, because if I put omega equal to 0, that means this is not satisfying, right? So omega equal to 0 is not a solution. So I can take omega common, like j omega common, right? This will be minus 2 omega square plus 4 equal to 0. So from this I get omega equals to 2 plus minus 2. I will ignore the negative solution. Omega belongs to real. So omega equals to 2. So one of the frequency of oscillation is 2. How can I satisfy? How can I verify it? So put omega equals to 2 in this equation, in the real part, plus 16 equal to 0. So if I put omega equals to 2, this will be 16 minus 8 into 4. 8 into 4 is 32 plus 16. That is equals to 0. So it is satisfying. So omega equals to 2 is a valid solution. Option B will be correct. Now of course I will not do it. You can compute the Routh table, you can solve it. That is the homework for you. But you will see it will be very lengthy. Computing the Routh table, it will not be super lengthy, but still it will be somewhat lengthy. Okay. So yeah, yeah, that's all basically. Yep. So omega equals to 2 is a solution. Let's now come to the next question. So here we have been given, consider an even polynomial. Okay, first of all, this system is not stable because I am missing few terms, right? Where k is unknown real parameter, k is real, unknown, complete range of k for which p of s has all of its roots on the imaginary axis. So what shall be the range of k for which p of s has all roots on the imaginary axis? So when do I get all roots to be on the imaginary axis? If I get some rows of zeros, right? So first I will solve using basics, then I will solve using Routh. So if all the poles are lying on the imaginary axis, then if I put s equal to j omega, it should satisfy, correct? So this equation will be converted into omega raised to the power 4 minus omega square plus 4 plus k equals to 0. It has to satisfy, correct? So x equals to omega square. So this will be x square minus x plus 4 plus k equals to 0. Okay, so this will be minus 1 plus minus b square minus 4 is 4 minus k upon 2a. So this will be 1 plus minus 3 minus k. Sorry, minus, so this is negative actually, minus 3 minus k upon 2. Now the thing is, right, I have told you this x value has to be a real number, right? It has to be a positive real number, right? Because it is omega square. If it is some negative, right, this will not be valid. So this has to be real, positive and real. So basically first thing is this has to be positive. It has to be positive. Otherwise if it is negative, omega will come out to be something imaginary. That is not possible because I have already considered this imaginary factor here with j. So this has to be positive. That means this term has to be positive. That means 1 plus minus 3k has to be greater than 0. That means 1 plus 1 has to be greater than under root minus k. So if I square on both sides, right? So both are positive, so I can square it. Basically square also will be both same. I can square both sides. This will be 1 greater than minus 3 minus k. So k has to be greater than minus of 4. So if k is greater than minus 4, this thing will always be positive, right? We can see, right? So that is one of the conditions for k. K has to be greater than minus 4. What about other condition? So I can choose the other root as well, right? I can choose this root as well, which has to be greater than 0. So if I choose this one, that is 1 minus 3 minus k, this has to be also greater than 0. So from this will be 1 greater than, okay, this will get the same condition only, right? Oh, sorry, I've chosen the positive. If I take it on the right hand side, this actually will be negative, but if I am squaring it, anyways I'm getting one condition only, so it does not matter. Yeah, if I'm squaring basically, right? So it does not matter actually. Okay, first of all, we'll anyways neglect this. Okay, no, if I have to add, this has to be positive. Okay, actually this will be a bit difficult for us to solve using basics. Maybe it's better if we solve using Routh. Okay, whenever you are stuck, right, you can always take help of Routh. So let me plot, write the Routh table s raised to power 3 s square s raised to power 1 s raised to power 0. So s raised to power, this is s raised to power 4 0, sorry, not s raised to power 2 is there, then this is 5, and then like because all the powers are reducing by 1 anyways, like 2, right? So all the terms are here, 4 plus k, and already I'm getting a row of 0 because all the other terms, right, s is cube, s raised to power 1, all are 0. So already I'm getting a row of 0. So this is my auxiliary equation. So this, right, I will replace my auxiliary equation is this, right? This is my auxiliary equation basically. So what will be the second row? Second row, this will be, if I differentiate this, this will be 4 s cube plus 10s, that's all, right? So here, right, this will be 4, this will be 10. Now if I continue here, this will be 4 minus 5, 20 minus 10 divided by 4, right? 20 minus 10, so it is 10 divided by 4, 10 divided by 4 is 2.5, and this is 4 plus k, and yeah, this will be 0. So this will be basically, okay, let me solve this. This will be difficult. This will be 10. Okay, this will be difficult, right? Just give me 1 second. Let me solve this. 10 minus 10 minus, so 10, hold on a second, 4 divided by 2.5, 1.6, 1.6 into this, right? That is, so like you can compute the Routh table. I'm just doing this in my mind. So 4 into this, 6.4 minus this is 1.6k. Okay, and like this is basically the first element actually, because this element is inverse 0, right? Why? Because this is 0, so I will copy this, this will be 0. So again, if this is 0 now, I will directly copy this. So right from this, right, this is 4 plus k. Okay, now all my poles must lie on the imaginary axis, so there must not be any poles on the right hand side. So if there are no poles on the right hand side, that means all this is positive, this is positive, this is positive, this I have to check whether this is positive or not, this also I have to check. So these two rows also must be, the first element must also be positive. So basically 4 plus k must be positive, so k will be greater than minus 4. Okay, and here this also has to be positive, 10 minus 6.4. So 10 minus 6.4 is nothing but 3.6 minus 1.6k. This also has to be positive, correct? So from this I can get a relation k must be less than 3.6 by 1.6. So if I divide by 4, right, this will be 9 by 4. Yeah, k must be less than 9 by 4 and k must be greater than minus 4. I think there was an option there, I forgot to copy the options, but your range of k would be k less than 9 by 4, 9 by 4 and k greater than minus 4. So of course, like you can solve this using basics, but I'm getting stuck here. Like there is something that I have to figure out. So whenever you are stuck, right, in the exam as well, if you are stuck, go with the general method. Okay, I was trying to do a bit of trickery here, but I was not able to do. So I stopped and I went with the general method. That's it. Let's solve the next question. So yeah, this is the next question. So the open loop transfer function of a unity feedback system is given by this. G of s is this, the range of k for which the system is stable. OLTF is given, right? So what will be my CLTF or characteristics equation? It will be s square. So simply it will be 1 plus, it is a unity feedback system, right? Nothing is unity feedback system, negative feedback system. So this will be actually s square plus 4s minus 5 plus k. Basically for a second order polynomial, we know basically all the coefficients must be positive. So minus 5 plus k must be positive. So k has to be less than 5. That's all. Pretty straightforward. I hope, like, sorry, k has to be not less than, sorry, k has to be greater than 5. Pretty straightforward, but again you can make some silly mistakes. Just be careful. So this is the solution. Let's move on to the next question. So the number of zeros of the polynomial in the right hand plane. So basically the number of zeros of the polynomial in the right, zeros basically mean whenever this polynomial is 0, that's all. So zeros of the polynomial. So whenever they are talking about poles of a polynomial, right, they are talking about the denominator. Whenever they are talking about the zeros of a polynomial, that means they are talking about the numerator. When the numerator goes to 0, that is what they mean by zeros, and by poles they mean whenever the denominator of a polynomial is going to 0. That's all. So how many roots are on the right hand side? Simply we can use like you can use Routh-Hurwitz criterion, or we can use internal product, external product. If I use internal product and external product, this will be 2 into 5, right, internal product, and your external product is equals to 80, right? So your internal product is less than external product. That means your system is unstable. That means there are many possibilities. There can be 3 poles on the right hand side. There can be 2 poles on the right hand side. There can be 1 pole on the right hand side as well. All these are valid possibilities. Yeah. Is this no? Actually, there cannot be. There can be 1 pole on the right hand side. Yeah, that is a possibility. What about 2 poles? And that is also actually that is also a possibility, right? There can be 1 left hand side pole. So simply you have to actually solve like the Routh table. So this will be s raised to power 1. This will be s raised to power 0. This will be s cube 1 5 0. This will be 2 80 and 0. This will be 10 minus, so this comes out to be negative, right? 10 minus 80 minus 70 divided by 2, that is minus 35, and simply this will be 0. Simply I copy this is 80. So how many sign changes are there? There are, this is plus plus minus plus, so 1 sign change, 2 sign change, 2 sign change, 2 sign changes. So there will be 2 poles on the, sorry, 2 zeros on the right hand side, right up plane. Okay, let's solve the next question. So we have been given this next question. Consider a unity negative feedback system. This is the G of s. The impulse response of the closed loop system decays faster than e raised to power minus t if, okay, it decays faster than e raised to power minus t. That is actually a bit interesting question. It decays faster than e raised to power minus t. Very, very interesting question. Okay, so here, right, they are asking us that it will decay faster than e raised to power minus t. That means if impulse response is decaying faster than e raised to power minus t, that means one of the pole must lie around, like one of the pole must be between this region, right? One of the pole has to be in this region, because if it is decaying faster, that means the this uh, time constant will be much smaller. Tau is smaller. If tau is smaller, right, Okay, sorry, if tau decays faster, oh sorry, it will not lie, sorry, if like it is decaying faster, right? If it is decaying faster, right, that means your settling time is smaller. Settling time is smaller. If your settling time is smaller, right, that means your time constant is smaller, because settling time is directly proportional to time constant, it is 4 tau. If your tau is smaller, that means your, what is tau? Tau is the inverse, magnitude inverse of the negative real part of the pole. So inverse of the pole is smaller, that means pole is larger, it is more on the left hand side of the s equal to -1 plane. So here, right, we have to find out the condition for k for which all my poles are lying on the left hand side of s equal to -1, so that all the poles are decaying faster. So this is the concept of mapping. Very interesting question. Directly they have not asked you, but indirectly they are asking you, find out the condition of k for which all the poles are lying on the left hand side of s equal to -1. So s equal to -1, I have to apply the condition of mapping of z plane. So s equal to -1, that is s plus 1 equal to 0. So s equal to -1 is z equal to 0. So I will replace 0 with z. So s plus 1 equal to z. So s will be equals to z minus 1. So that is the replacement that I will do. First of all, let me write the characteristics equation. This will be k upon s into s plus 2 plus s plus 3, that is s plus 1 into s square plus s plus 1 into s square plus 5s plus 6. This is equals to 0. So this will be s cube plus 5s square plus 6x plus s square plus 5s plus 6 plus k equal to 0, right? So your equation would be s cube plus 6s square plus 11s plus 6 plus k equals to 0. Okay, so yeah, that's all. So now, right, now we will use the replacement s equal to z minus 1. So this will be z minus 1 whole cube plus 6 into z minus 1 whole square plus 11 into z minus 1 plus 6 plus k equal to 0. So this will be z cube, okay, z, what is the formula for z minus 1? I have also forgotten. Okay, what we can do, right, we can do this simplification. So if you forget, like, this is the formula actually, so you can write it like this, that it will be z cube plus 3z into minus 1 into z minus 1 plus minus 1 whole cube. That's all. That's how I used to remember this formula. So if I solve this, this will be z cube minus 3z square plus 3z minus 1. That's how I remember it. Okay, that is the thing that I do to remember this formula. So this will be minus 3z square, okay, minus 3z square plus 3z minus 1 2z plus 1 plus 11z minus 11 plus 6 plus k equal to 0. This will be actually minus 5. This I can directly write to be minus 5. That's all. So yeah, here, right, minus 3 and this will be minus 12. Okay, minus 3, sorry, this is square only, right? Minus 3 plus 6, minus 3 plus 6, so this will be plus 3z square. That's all. This will be plus 6 minus 12, so this is minus 9, minus 9 plus 11, So it is plus 2z, and the constant term, this is minus 1 plus 6, that is plus 5, plus 5 minus 5, that is 0 only, right? So this will be plus k. So what is the condition for k, right? For all the it has to decay faster than 1. Basically all the poles must lie on the left hand side of minus 1. All the poles must lie on the left hand side of z equal to 0 plane. So let us find out that condition. What is that condition? The condition is basically internal product must be greater than external product. So 6 must be greater than k. So k must be less than 6. That is a simple condition. So option A is satisfying. One more thing is there, that all my coefficients must be positive for it to be Hurwitz polynomial. So k must be greater than 0. So the range of k is between 6 to 0, right? So what is the valid range that is given to me? So this is not valid, right? It is greater than 6. This is also less than 0, not valid. This is also less than 0, not valid. Only this one is valid. So option A will satisfy. So that's the beauty. This question is actually very beautiful. This question is very beautiful. Okay, very tricky, not that simple. It is not that easy. Another way to solve this is you can take help of Routh-Locus. That is the next chapter. In Routh-Locus, you will be able to find out which poles are lying on the left hand side of s equal to minus 1. All those things you can find, okay, with the help of Routh-Locus. So with Routh-Locus as well, you can solve it. So you can search GATE 2024 control system solution mapping. So I have solved this using Routh-Locus as well there. Okay, so this can be solved using Routh-Locus as well as this Routh-Hurwitz criteria. Let's solve the next question. Okay, this is the next question. So consider this polynomial. L is the poles number of roots on the negative, that is the left hand side. Imaginary, I is imaginary, R is on the positive, real, on the positive side. Okay, so they are asking me what is L, I, R, these values. Simply we have no other option but to use Routh table. So this will be s raised to the power 5, s raised to the power 4, s cube, s square, s raised to the power 1, s raised to the power 0. This will be 1, 3. So 1, then 3, then 2, and that's all. 1, 3, and then 2. Then this will be 7, then minus 33, then minus 40. So 7 minus 33, then minus 40. That's all. And yep, that's all. So this will be 21 minus 33, that is plus 33, that is 54, right? 54 by 7. 21 plus 33, 21 plus 33, 54 by 7. 54 by 7 comes out to be something very weird value, 7.7, right? 7.714. Let me keep enough space here. So you also, while drawing the Routh table, give enough space. Okay, you need to give enough space. And this will be 7 into 2, 40, 14 plus 40 divided by 7, which is basically 50, again 54 by 7 only. So it is 7.714 only, and this will be 0. So what will be this value? So these are all same coefficients, right? Simply you can ignore this because you are dividing by this. It will be simply minus 33 minus 7. That's all. You can solve this. You will get minus 40 only. You can solve this, okay? Because these will be cancelled. These terms will be cancelled. Now, as I have 0 over here, I can just copy and paste. This will be also minus 40. That is interesting. Now I will get a row of 0 next. You will get a row of 0 here, right? This will be row of 0. So your auxiliary equation, I get an auxiliary equation, that is minus 40 square minus 40 equal to 0. So a square is equals to minus, this is s plus 1, 1, that is s equals to plus minus 1. So I see not plus minus 1, plus minus j. I see I have two imaginary roots, of course, and the derivative of this, that is minus 80 s. This will be my next row. This will be minus 80. This will be 0. and 0. So if I have 0 here, I will just simply copy and paste. So this will be minus 40. So how many sign changes do I have? So this is positive, 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 negative, negative, negative. So I see one sign change, that's all. I have one sign change. So I will have one pole on the positive side, right? So one pole on the positive real side, two poles on the imaginary axis, and two poles on the left hand side. Okay, because I have only a one row of 0 and the order of that is only 2, right? So I will get 2 roots of this auxiliary equation. I will have 2 poles on the exactly at the j omega axis. The rest of all the poles will be on the left hand side. So option A will be your correct answer for the question. Let's solve the next question. This is the next one. So here we have given this g of s. The closed loop system is shown below. It is stable. So basically they are asking for stability. So what will be the characteristic equation? It will be 1 plus OLTF, right, equal to 0, right? Is it OLTF? No, it is 1 plus, yeah, it is OLTF only, 1 plus g of s. Yes, it is 1 plus OLTF only, equal to 0, correct? So this will be 1 plus, okay, g of s is this, right? So k into s minus 1 divided by s plus 1 into s plus 2 equal to 0. So this will be s square plus 3s plus 2 ks minus k equal to 0. S square. So like basically it is a second order equation. So I can tidy this one up. So this will be 3 plus k into s plus 2 minus k equal to 0. So basically all the coefficients must be positive. Like that was the condition for a second order equation. So 3 plus k must be greater than 0. So k must be less than minus 3. That is one condition. Okay. Hold on a second. 3 plus k. K is minus k. So this will be s square plus 3s plus 2. That is correct. So 3 plus k must be positive. Okay. 42 is stable. 3 plus k must be positive, and your this 2 minus k, right, must also be positive. Basically your k has to be greater than 2. So we are not even getting a valid range. So it is okay. We're not getting a valid range. Something am I doing, missing something? Hold on a second. Oh, whatever. 3 plus k has to be positive, right? So k has to be greater than minus 3. So basically for stability these two conditions need to be satisfied. What is the common region? Basically for stability k is greater than minus 3, right? So k greater than minus 3 includes, like let's say this is the minus 3 point, it includes all these points. So it includes all these points, k greater than minus 3, and k greater than 2 includes these points. So of course I have to choose the common region because we have to satisfy both the conditions. So both the conditions are satisfied here. K greater than minus 2. So k greater than 2. So k greater than 2 system will always be stable. So k greater than 2 stable system is stable. Yes, option A is correct. It is unstable for k greater than 2. Incorrect. It is unstable for all k greater than 2. 1. No. It is unstable for, hold on a second, 3 plus k has to be greater than 0. So k has to be greater than minus 3. Okay, so what am I doing? K has to be, so if I take this k on the other side, k has to be less than 2. So the range of k, right? Sorry, I'm sorry, extremely sorry. So that was for the other, like some other condition. Range of k is, k has to lie within this range. K has to be greater than minus 3 and less than 2. Then only system will be stable. Otherwise system will be unstable. So stable for all k greater than 2? No, it is not stable. It is not stable for any k greater than 2. This option is incorrect. Unstable for all k greater than 2? Yes. If my k is greater than 2, it will be always unstable, right, for any value. So unstable, this is correct. Unstable for all k greater than 1, no, because between k 2 to 1 my system is stable, so it is not unstable for all k greater than 1. Okay, so this option is wrong. Stable for all k greater than 1, again not for all, it is only stable between 1 to 2, right? Other, if it is greater than 2, it is unstable. So this option is also incorrect. So your option B will be your correct answer for the question. Let's solve the next question. So for the transfer function g of s, this, the number of zeros lying on the left hand side. So they are discussing about the number of zeros. This is my transfer function, they are discussing about the number of zeros, not the poles. Okay, so let me write, zeros are basically roots of my numerator. Okay, so what is the numerator? This is basically, if I solve this, right, this will be s cube plus 5s square plus 3s plus 22 plus 2s minus 1 upon s cube plus 5a square plus 3s plus 22. So numerator, right, I have to discuss about the numerator, not the denominator. So the numerator is this, I will copy this, copy the numerator, and it is a third order equation, so it becomes very simple for me, right? So let me simplify this actually. So I have to add, okay, we should not go into the next page. So this is this should be 2s minus 1. So if I simplify this further, so yeah, the number of zeros lying on the left hand plane. So we have to solve the Routh table because they're exactly asking me how many roots are lying on the left hand side. So we have to solve for the Routh table. So I have s cube here, 5 here. Actually, what I can see, internal product is greater than external product, right? So system will be stable. So there are no roots that are lying. So there are no poles that are lying on the right hand side actually. But actually, how many? So there can be complex. There can be imaginary poles as well, right? So for that, I have to actually solve. I have to solve the Routh table. Otherwise, I will not be able to directly conclude. If instead of left half, right, it would have asked right half. Then I got to directly set, because the system is stable, definitely I can say, okay, it is not even marginally stable, right? Because if it was marginally stable, then there would have been imaginary roots. So internal product is greater than external product. So all my roots actually are lying on the left hand side. So option 3 will be correct. Option D will be correct actually. But let's solve. Because if it was marginally stable, correct, then internal product was equal to external product. But that is not the case here. Internal product is greater than external product. So all my poles actually will lie on the left hand side only. All my poles will lie on the left hand side only. Because it is stable, right? It is not marginally stable. It is absolutely stable. So all the poles has to lie on the left hand side. We can confirm that with the Routh table, obviously. 1, this will be 1, 5. This will be 5 and 21. So this will be 25 minus 21, that is 4 by 5. So this will be 0. So this will be 21. So there are no sign changes. So of course, system is completely stable. There are no right hand side poles and there is no ROZ. So there are no imaginary poles as well. So option D will be your correct answer for this question. With this, we end our Routh-Hurwitz criterion. Now we will start off with root locus. Let's begin with root locus. So from the name, you can understand that what is locus? Locus is basically plot. Okay, plotting of any variable that is varying, changing, a trace. And root means roots of my CLTF. So root locus basically means it is the loci or trace of poles of closed loop transfer function. So we'll plot the trace of closed loop poles. Now you will say, sir, how can I plot the trace of closed loop poles? They will not vary, right? If I have this equation, let's say if my g of s is 3s plus 1 upon s plus 2 into s plus 3 into s plus 4, this is my root locus. So I can say that my closed loop poles will be a constant number, right? It will not vary. But how will you plot the root locus? Like how will you vary the closed loop poles? Basically, we want to see if my OLTF is not a constant function. It is a function of k, where k is any constant number. For now, you will assume k to be any positive constant number. I mean not constant, sorry, k to be any positive variable. Real. It can only take real values. K can only take real values. So we will vary our k, and with the variation of k, we will observe how does my closed loop pole vary. So we will find out the condition of k, and also we will find out many different values of k for which my system will be underdamped, it will be overdamped, undamped. So that is what we will do basically. That is the crux. Now mostly, okay, now k is just a system parameter, it is not the desiccant. In this case, if your OLTF is in the standard format, it can be a desiccant. But sometimes, let's say if I have poles at the origin, then k will not be a desiccant. K is just a system parameter. K is not a desiccant. Sometimes k can be desiccant, but not always. I have told you, right? If it's a type 1 system, if it's a type 2 system, then that k is not the desiccant. Okay, k becomes the desiccant when my OLTF is in standard format. Okay, so just one thing to be careful on, right? Now there are many things, like my transfer function can be two things. Either it can be a proper transfer function or a improper transfer function. What do I mean by proper and improper? Proper meaning if the number of open loop poles are greater than number of open loop zeros, then it is called as proper transfer function or practical transfer function. Why is it called practical? Because if you see, if the, let's say, number of zeros is greater than number of poles, then what will happen? Let's say this is my OLTF. OLTF g of s is equals to s. Now, if OLTF g of s is equals to s, do you know what is this in time domain? It is a differentiator, right? And to basically design a differentiator, it is very difficult. Why? Because the differentiator, what it does, output y of t is equals to limit as t tends to 0, it is x of t plus some delta t minus x of t upon delta t. So this, right, this is what this, right, x of t plus delta t, meaning I have to predict the future. So here I have to predict the future. That's why it seems like it is an impractical system. Although we can design differentiator, we can have different ways to design a differentiator, but in real life, like this seems like impractical design, because we have to predict the future. That's why these are called improper transfer functions, and generally we will be discussing about proper transfer functions only. So mostly, but root locus is applicable for anything. Okay, because root locus is just the plots of any equation, okay, with respect to any parameter, system parameter k, or any variable that is varying. So in our case, case 1, you will consider k to be non-negative number. It can be 0 as well, no problem, right? But it has to be non-negative number. That is the first thing. Now let us discuss how can you plot the root locus. Okay, so here, right, let's say I have this OLTF, and let's say, okay, let me keep it a, k upon s plus 2. What will be the root loci? Because basically if I vary my k, how will the closed loop poles vary? So what is my characteristics equation? So this will be 1 plus g of s h of s, that is s plus 2, equals to 0. So this will be s plus 2 plus k equals to 0. So basically if I vary my k, right, my poles is also varying linearly. s equals to minus 2 plus k. So basically k is any positive real number, right? So if k is any positive real number, so I have a pole at s equals to, if whenever my k is 0, if my k is 0, right, where do I have the pole? Okay, sorry. So what is the pole location of OLTF? At s equals to minus 2, correct? This is the pole location of my OLTF, correct? Now as I increase my k, right, now when my k is infinity, okay, hold on a second. So yes, so when my k is 0, right, when my k is 0, what is the closed loop pole? It is minus 2. So when your k is 0, your location of closed loop pole is also minus 2. Now when your k is increasing, right, let's say k becomes 1, 2, 3, so your s becomes, this becomes minus 1, then it becomes 0, then it becomes, sorry, not 0, sorry, so this will be minus 1, sorry, this will be, when k is 1, this will be minus 3, this will be minus 4, minus 5, and so on. So it is increasing in the negative direction. So if I increase my k, the value of my pole is going on the left hand side, okay? And if I keep on increasing my k, right, my s also will keep on increasing on the negative direction. So I will have a, this is called as a virtual zero, okay? I'll explain these terms, but don't worry, they will not ask you what is virtual zero, but these are the notations that we use. So this is called as a virtual zero when my k is tending to infinity. So k is equal to infinity. This is the point. And this point is when my k is equals to 0. So my root locus actually will start. So the closed loop pole will actually start from the closed loop open loop poles. The closed loop poles will start from the loci of the closed loop poles will start from the location of open loop poles when my k is 0, and they will terminate on virtual 0. These are called as asymptotes because of course I cannot touch them. Asymptote is something that is increasing, negative, I cannot touch them, okay, but they will touch the asymptote at k equals to infinity. These are also called as virtual zeros. Why are these called as virtual zeros? So basically, right, if you see here that if I solve this equation, this will be my CLTF, right? CLTF would be g of s upon 1 plus g of s. So that would be g of s is this, right? K upon s plus 2 plus k. This is my CLTF, correct? So basically whenever my k is infinity, right, this terms will be dominating. Instead of this term will be dominating. So it behaves as a 0. That's why these are called 0. So there are many things as well. I will explain those things. I think yeah. Whenever, okay, I think we have a where is my 0? Yeah, here. So let's say if this is my transfer function, right? This is my OLTF. Okay. So whenever k tends to infinity, right? Whenever k tends to infinity, this term is neglected. Okay, I can divide by k on both sides. This term is neglected. So s becomes alpha. Whenever k is infinity, what we can do, we can divide by k on both sides. So this term will be neglected. S will be alpha. So basically, whenever k is going to infinity, it is touching a 0. So actually what happens, if let's say I would have had a 0. So let's say if my transfer function OLTF would have been 1 plus k into s plus 1 divided by s plus 2. Okay, this will be a better example. This equals to 0. So if I want to plot the root loci, right? So this will be s plus 2 plus k into s plus k equals to 0. So this will be s into 1 plus k plus 2 plus k, correct, equal to 0. So my pole location is minus 2 plus k upon 1 plus k. This is my pole location, right? So if you see, whenever my k is 0, so my s is equals to minus 2. That is nothing but my open loop poles. And whenever k is infinity, so if k is infinity, right, k is tending to infinity, s will be equals to, there is a minus sign at the in front, so it will be minus 1. So whenever k is infinity, it is minus 1. So this is nothing but the 0 location. So whenever k tends to infinity, we will touch 0. Okay, our root locus will touch 0, and whenever k is 0, our root locus will touch pole. That's why in this case, in this example, because I did not had any 0, so it is just a virtual 0. Okay, that's why it is called virtual 0. That's it. So at k equal to infinity, we will touch a 0, but that 0 does not exist, so it is called a virtual 0. That's all. Okay, so that is one thing, right? Now this is the root loci for this particular function. What about what will be the root loci for this particular function, for this particular OLTF? So if I plot this, right, I will have a pole at s equals to -2. I will have a 0 at s equals to 1, -1, right? And I know that of course at k equal to 0 I will start from my pole, and at k equal to infinity I will end, correct? So basically I will have to move in this direction, because what do I observe? I observe that my pole is always a negative number, because k is real, it will never be complex. S will never be complex, S will always be real, and as k are both are positive and these is totally positive and there is a negative sign, so overall the pole location will always be negative. So I start from -2 and I will end at -1. That's all. Okay, that's all. So yeah, that is the trace of my root locus. That's how you plot the root locus for a basic first order system, but of course there are some rules, certain rules that we'll discuss for second order systems. Okay, this was a very simple example. Okay. So all these things will come about this. Let me first check for a basic example. What is a basic example? This is a second order system, right? So first of all, whenever this is a second order system, first what should be your task 1? Step 1 will be to identify the, this is my OLT, right? So identify the open loop poles and the open loop zeros. First task is identifying the open loop poles and open loop zeros. That is your first task. So if it's a what is the open loop poles? It is -2, -4, and open loop 0 is -8. So first of all, you will draw the pole 0 diagram. Sigma j omega, and I will draw the pole 0 diagram. So here I will have two poles, that is at s equal to -2, s equal to -4, and at s equal to -8. Okay, this is a 0, sorry. So we know one thing, that so in this case, right, we had only one branch, single branch. In this case also we had only one branch. So now you have to identify how many branches you will have of your root locus. How to calculate that? Number of branches will always be equals to either number of poles or number of zeros. Whichever one is greater, your number of branches will be equal to that. So in this case, how many number of branches I will have? In this case, as I have, like, number of poles is 2, number of zeros is 1. So total number of branches will be higher of the two. So number of branches B will be maximum of P comma Z. So it is 2. So my root locus will have two branches. Okay, like this will be one of the branch. I can already tell you, because it will start from a pole and it will terminate, and there will be a other branch as well. But how do I draw that branch? Okay, actually this will not be a branch, sorry. This will not be a branch, I mean I'm wrong, this will not be a branch. So there will be two branches, certainly there will be two branches, but how do I draw the branches? That is interesting. So how to draw the branches? Now your step 2 would be to start plotting the root locus. Okay, so locate the root locus on the real axis. So on the real axis, always identify a point. Let's take for example this point. Let's understand whether this point in the real axis will lie or not on my root locus. How to identify that? If you have odd number of poles plus zeros, so if I add all the poles on the right hand side of my point and it comes out to be odd, that means this point will lie in the root locus. Let me take an example. So how many pole 0 I have on the right hand side? 3. P plus Z is 3, which is odd. So that means this point actually will lie in the root locus. So if I extend, right, if I extend till minus of infinity on the real axis, all these points on the right hand side always have 3 poles. So always the sum of pole plus 0 will always be 3. So all these points will be lying in the root locus. So I will have a virtual 0 actually here. Okay, although I cannot, let me draw it. I will have a virtual 0 here at k equals to infinity. This will be a virtual 0, and here also of course my root locus will terminate in a 0, actual 0 at k equals to infinity. Now what about this point? If I check here, right, how many poles 0 I have on the right hand side? 2, which is even. 2 poles, which is even. So these points, all these points will not lie on the real axis, on the root locus. All these points will not lie on the root locus. Again, if I consider this part, if I see on the right hand side, how many poles I have? Pole plus 0, 1. So which is odd. So definitely all these points will lie in the root locus. Now you will say, sir, how are you saying this will lie in the root locus? So there is a derivation. Of course, I have done the derivation. We use, like, for a particular point to lie in the root locus, right? We have to solve the characteristic equation of the root locus. It must satisfy this equation. If I solve this equation, my g of s h of s is -1. So there are two conditions from this, right? As it is like in the complex domain, so we can say the magnitude must be 1 and the phase must be -180, like multiple of -180, correct? So not multiple, sorry, odd multiple of -180, odd multiple of -180. So if you solve this particular condition, right, you'll figure out that you will see that for this condition to be satisfied, this condition has to be satisfied. Basically, the sum of roots plus poles must be odd. Okay, so yeah, that there is a derivation. We don't want to go into the derivation. I just given you a intuition. How can you understand this rule? So this is a very important rule. So this is what you have to remember actually. So we identified. So if I consider this part, right, the right hand side of -2, do I have any poles and 0 on the right hand side? No. So it is 0. Is 0 odd? No, 0 is not odd. So definitely these points will not lie in the root locus. So we figured out which points are lying in the root locus on the on the real axis basically. So we figured out the points that will lie on the root locus on the real axis. But one thing is there, that you have to satisfy this as well, right? What do you have to satisfy? You have to satisfy that like your roots can be complex conjugate as well, so they can lie here as well, right? So we have not come to that point. We only considered the real axis. So in the real axis, wherever my root locus will lie, that we have plotted. What about this part, right, complex part? For that you need to understand the angle of asymptotes. So how do you calculate asymptotes? So these are these virtual zeros, right, wherever my root locus will terminate, these are called as asymptotes. The virtual zero, the angle of virtual zero with respect to the positive x-axis, right, that is sigma axis, will be my angle of asymptotes. Okay, so what is the angle of asymptote here? One asymptote is there on the negative real axis, right? So what is the angle with respect to the positive x-axis? It is 180. So your angle of asymptote should come out to be 180. Now how would you calculate this without drawing this? So how to calculate? So again, these things you have to remember. Unfortunately, these things you have to remember. Of course, there is derivation. These are the derivations. I've already, like, how to solve for angle of asymptotes. There are derivations, but of course we don't have time for derivations now. We have to come to the conclusions. So the formula for angle of asymptotes is simply theta asymptote. Okay, it is -180 plus -180. It won't matter actually. Anything works. Plus -180. Odd multiple of -180. Okay, odd multiple of -180 divided by the poles minus zeros. Okay, this is the formula for angle of asymptotes. This you have to remember. No other option but to remember. So what is angle of asymptote? Angle of asymptote is basically this formula. So in this case, what is the angle? -180. So let us confirm whether this formula works or not. So till what point I will go, right? This 2k plus, so this k, right, k will start from 0. Okay, and it will go 1 2 3 and it will go till the point p minus z minus 1. Basically whatever is the difference of poles. So in this case, what is P? Number of poles is 2, number of zeros is 1. So P minus Z minus 1 would be 0. Okay, so for only I will solve for k equal to 0. Basically, it means I will have only a single asymptote. That you can see from here itself, right? I only have a single asymptote. The other is a actual 0. This is a virtual 0, correct? So basically, the difference between pole and 0, because my root locus will always start from the roots of my OLTF, and they will always terminate on the zeros of my OLTF. Because I did not have enough zeros, I had two locus, two branches that started from pole, but I did not have enough zeros. Then this was a problem, right? That's why I had to make a virtual 0. That's why it is an asymptote. So how many asymptote I will have? One asymptote for k equal to 0. So if I put k equal to 0, this will be minus 180 minus 180 okay, just give me 1 second. Yeah, minus 180 divided by pole minus 0, that is 2 minus 1. So it is minus 180 only, right? So angle of asymptote will be minus 180, and isn't that what we discussed already? So this was one thing regarding angle of asymptote. Now there is one more thing regarding centroid. Okay, centroid will come in the next example, don't worry. Centroid is the point where my asymptotes intersect. Let's say I had two asymptotes, one asymptote here, one asymptote here, right? Two asymptotes. So where will the asymptote intersect in the real axis? Okay, if I touch a line, straight line joining the two asymptotes, right, where will they intersect in the real axis? That is given by the centroid. So centroid will be basically the sum of all the poles minus sum of real part of all the poles minus sum of real part of all the zeros, okay, divided by number of poles minus number of zeros. What do I mean by real part of poles and zeros? So basically, let's say if I have two poles that are not on the real axis, let's say I have one pole at minus 1 minus j, another pole at minus 1 plus j. So I have two poles. So what will be the sum of real part of pole? Sum of real part of pole would be this first pole real part, that is 1 minus 1, sorry, and what is the real part of this? That is also minus 1. So sum of real part would be minus 1 plus minus 1, that is minus 2. So you will ignore the imaginary part. So you will consider only the real part. Okay, that is the formula for centroid. In this case, right, if I calculate this, if I use the formula, so what is the sum of real part of poles? It is minus 2 plus minus 4. And what is the sum minus of zeros? It is minus 8. I have only a single zero upon number of poles minus number of zeros. It is very easy to remember, right? P minus z, sum of P minus z by P minus z, not that difficult to remember, upon P minus z, so 2 minus 1. So this will be minus 6 plus hold on, yeah, minus 6 plus 8, that is 2 upon 1, that is 2 only. So the centroid is at 2. Basically there is only a single asymptote, right? So centroid actually is not like significant in this case. If I have only a single asymptote, right, then centroid does not come into picture. We'll discuss about the centroid with a proper example. Okay, here we will not understand the significance of centroid because I have only a single asymptote. Centroid in US is not defined for a single asymptote. It is defined for two asymptote. Where will the asymptotes join basically? Okay, if I take a line and join all the asymptotes, where will they intersect in the line intersect in the real axis? Now what will happen? Actually this root loci, right, one branch will start from 4, other branch will start from 2, and both of them will actually intersect. So one branch will go along this direction and end at minus 8, other branch will go along this direction and end at virtual 0. So this will be the actual root locus. But you will say, how sir have you plotted this thing, right? How it will be circle? So there is a derivation of course that it will be a circle only. So that derivation is also there, but in our course we will not be able to derive it because that will again take some time. But for sure this will be a circle, that I know. What is the center of the circle? The center of this circle will always be the rightmost zero. Although pictorially it is not, you cannot be able to understand this, but the center of this circle of root loci will always be the rightmost zero. So rightmost zero is this one. So, but sir, yeah, just trust on me that this will be the location, this will be the plot of root locus, but I have to find out these 2 points. This right here, I see the both the root locus are breaking out, touching each other and then breaking out from the real axis. So this is actually called as the break away point, BAP, and this is called as the break in point. Okay, BIP and BAP. Now, how to calculate this BAP and BIP? Again, there is a proof that breakaway point and break-in point, both this occur whenever the value of k is either maxima or minima. Okay, so basically, right here my k starts from k equal to 0, correct? Slowly the value of k increases, so they will, both of them will come here, and this will be some value k breakaway point, and at this particular point, right, this will be a local maxima, because from both sides I'll come, value of k increases. So on the real axis this will be a local maxima. Okay, why local maxima? Because in this whole region, everywhere, let's say increase from k equal to 0 to 0.1, so my root locus moved here, my root locus moved here, then I increase from 0 to 0.2, my root locus moved here, this moved here. Slowly if I keep on increasing, right, at certain point they will meet each other, after that they will diverge, right? So as soon as they will diverge, right, so now my root locus is not on the real axis. So on the real axis the value of k is maximum at breakaway point. So that's why if I am able to write my k as a function of s, and if I differentiate my k with respect to s and equate it with 0, the point of maxima will give me the value of k, and also the breakaway point. I will also be able to calculate the breakaway point. I will show you. Of course, again there is a proof. I have proven it in my full course, but of course again we don't have time. Similarly, here what is happening? Here the value of k is infinity. Here the value of k is infinity, very large. Here it just arrived in the real axis. After this, the value of k will only increase, right? If I keep on increasing my value of k, it will only shift on the real axis. So in a break-in point, the value of k will be minima on the real axis. That's why it is called as a local minima, not global maxima or global minima. These are my local maxima, local minima. So on the real axis, the value of k will be minimum, because beyond this point I am just increasing my k, right? Here k is infinity, here k is infinity, but here value will be least. After that it will only increase. That's why in a break-in point I will get a minima, in a breakaway point I will get a maxima. If you forget this, you can always plot the root locus and understand conceptually what is happening. So of course there is derivation, but without derivation also we can understand intuitively what is happening. So our next task after asymptote would be to calculate the breakaway and break-in points. So here, right, there will be both a breakaway point, this will be my breakaway point, and there will be a break-in point. How do I calculate the breakaway and breaking point? I have told you that my k will be local maxima or local minima. Okay, so what is my characteristics equation? It is 1 plus, this is my characteristic equation, right? Yeah, this is my characteristic equation. Now what is my k in terms of s? So k will be equals to minus s plus 2, or if I solve this further, it will be s square plus s square plus 6s plus 6s plus 8 divided by s plus 8. Now what we'll do is we will differentiate k with respect to s, because on the real axis, so s I am varying on the positive real axis. Okay, s is not a imaginary value, s is a real value, s is a real value. So after solving this, right, if you get s to be imaginary, right, that means you don't have any breakaway or breaking points, because we are varying our s in the real axis. That is what do we mean by local maxima, local minima, because beyond this point what happens here, these 2 points, right, yeah, k is increasing. Here let's say k was some 10, k was some 10. Okay, if I increase it to 11, what will happen? I will be in this region, right, I will be in this point. Then you will say, sir, how is this maxima? How is this maxima, sir? If here my k value is 11 and how is this maxima? It is local maxima. Local maxima on the real axis. On the real axis. Trust me, if you have already studied control system somewhere else, right, you will feel this is completely different. Okay, like if you have studied root locus previously, you will feel, what is this? My educator has not told this. Yes, because that was a different institute. They are also great, like they also do some hard work, but this is PrepFusion, right? And at PrepFusion, of course, you will get the best quality content. So this came after much research. Of course, like you, I also had the same doubts. So I cleared the doubts. What do they mean by maxima? Maxima basically means on the real axis, negative real axis, here the value of k is maxima. Of course, k value will increase here and here, but here my poles or roots are complex. Closed loop poles are complex, but I am not worrying about the complex numbers. Okay, I am worrying about the real axis. Same applies for the break-in point as well. So yeah, here, right, that's what I'm telling you. If you solve this equation and after solving for s, you get s to be imaginary, that means there is no breakaway or breaking point. Okay, so but here we will get some negative real values, so I will explain that as well. So let's see. So let's solve this. So if I differentiate my k with respect to s, so negative sign will be there, right, dk ds, negative sign will be there, so this will be minus of, okay, if I differentiate this, this will be s plus 8 whole cube, sorry, not 8 whole, so 8 whole square, this will be differentiation of the numerator, 2s plus 6, this will be s plus 8 minus, so anyways, right, the denominator does not matter to me actually, because I will equate this to 0, so denominator anyways will go down the drain. This will be s square minus 6s plus 8. Okay, this is anyways equal to 0, so what is happening, I am equating this to 0, so this is gone, right? So ultimately I will have to solve for this particular value, 2s plus 6 into 8, so this will be actually, if I take, this will be 2s square, 2s square plus 2s square plus 16s, 2s square plus 16s plus 6s plus 48 minus, this is s square plus, sorry, this will be minus as well, right, minus 6s minus 8, actually there is a bracket, right? Yep, so this is equals to 0, so if I solve this, this will be s square plus 10s, not 10s, sorry, s square plus 10s, sorry, s square plus 16s only, plus 48 minus 8, which is plus 40 equal to 0. So minus b plus minus b square minus 4ac upon 2a. So if I solve this, this will be 156, sorry, 1 not 96, I guess, 96 is, I think it is 14 square, right? So 256 minus 1600, oh, it is not 40 square. What am I doing? So it is 9.8 something, 9.8 plus minus, so I get two solutions. So the two solutions are this plus minus 16 upon 2. So one solution is 12 minus 12.9. Okay, another solution is minus, hold on a second, this plus minus 16 by 2 minus 3.1. In both the cases, my s value, right, is coming out to be a real number, negative, but it's a real number, that's fine. So both the cases s value is coming out to be real. So these are all, both of them are valid breakaway points. Both of them are valid breakaway points. So here, right, both of this will be valid. Also, you can get an idea. So which one will be a break-in or breakaway point? That for that there are two ways. Either you can double differentiate this function, basically differentiating this again, and then check the sign of that function. If it is positive, it will be minima. If it is negative, that will be maxima. I hope you know how to calculate maxima, minima. But the better way is to just check here, right? So my breakaway point has to lie between minus 4 and 2. So one of the solution, this solution is between minus 4 and 2. So of course this will be my breakaway point. I don't need to solve, right? So here, right, s equals to minus 3.1 will be my breakaway point. Okay. Hold on a second. And what about the break-in point? So s equals to minus 12.9 will be break-in, because I can see it has to lie between minus 8 and infinity. So it has to be lower than minus 8, which is one of the point is minus 12.9. So of course s equals to minus 12.9 will be my breaking point. That's how you can simply identify which is your breakaway point and which is your breaking point. Simple method, right? Now, what is the value of k? So one condition is, of course, this has to come, this locations must be valid. Basically, this must be real. Next thing is, the value of k after putting the break-in and breakaway point also should come out to be positive real number, because k was assumed to be a positive real number. So if you put this value minus 3.1, you will see that it is coming out to be positive. If you put minus 12.9, then also it will come out to be positive. I think we have already done that kind of thing. Where is it? This, lot of things. Okay. We have done a lot of things. Okay, like this is the plot of my, like, k, plot of k as a function of sigma. If I'm only varying the real part, right? So that is the plot. We'll get a local maxima basically. That's how we get the plot break-in breakaway point. Yeah. So we got these two poles and check. Yeah, we will check the value of k, right? So if I check the value of k basically at minus 3.1, it will come out to be a positive number 0.2. And if I check the value of minus 12.89, it will come out to be 20. So both of them are positive and real. So these are all my valid breakaway and breaking points. Also, you can understand, of course, with by seeing, observing the root locus simply that, okay, if I'm getting, so let's say if one of the solution here, right, was coming to be, it was also coming out to be real only, s equals to, let's say, 2. Okay, this you will encounter while solving questions. Now, if you get a solution is equal to 2, is this a valid breakaway point or break-in point? First of all, you can of course put the value of s equal to 2 in this equation and check whether your k is coming out to be positive real. Or easier way is to go to the root locus. You know your break-in point or breakaway point, breakpoints will lie either between -2 to 4 or between -8 to infinity, minus infinity. Okay, but this is s equal to 2, 2 is here. So these are not like, this is not a valid location, right? Not a possible location for breakpoints. So that solution will be incorrect. That's how you can simply reject a invalid break-in or breakaway point. Okay, that's all. That's the main thing basically. Okay. Now, few more things are there. I think. Yeah, that's all. I think that's all. That's all. So let's try to solve for few more cases. I think we have already plotted the root locus. Where is the root locus? This is my root locus, I guess. Okay, it's very lengthy. Okay. I think that's it. So for this, you will only need this much knowledge. Okay. So I had plotted in my MATLAB as well. In a full course, I plot like things in MATLAB. So in MATLAB as well, you can confirm, verify what is your root locus. Okay. Now you will say, sir, what is the advantage? We have been studying root locus for around 40 minutes, 40 to 35 minutes. What is the advantage of this? With the single graph, right, I can directly say for what value of k, my system will be underdamped, my system will be overdamped, my system will be critical damped. So with just one picture, I can directly say. Otherwise, you would have had to calculate. That is also not a bad method, but it will be a lengthy method. Okay, but here directly you can say, right? So when will my system be underdamped? When I have complex conjugate roots. So where do you see complex conjugate roots? This part, right? This part. And of course, yeah, one more thing I forgot to tell you regarding root locus, that if I'm plotting the root locus, right, in the complex plane, that means I must have it mirror image. So my root locus will be mirror image about the real axis. It has to be, because all my coefficients are real. If all the coefficients of characteristics equation are real, that means you will always get complex conjugate poles. There is no other possibility. If roots are lying in the complex plane, you will always get complex conjugate poles. So if one root is here, other root must be here. It has to be. If all the coefficients are real, remember, all the coefficients of characteristics equation are real. So that is the thing. So that's why your root locus will be symmetrical about real axis. That I forgot to tell you, but now I have told. Okay. So what is the location of, what is the value of k for which my system will be underdamped? So we found that at k equals to 0.2, we get a break-in point, sorry, breakaway point, and equals to k equals to 20, we get a breakaway point, sorry, break-in point, right? So in this range from k equals to 0.2 to k equals to 20, my roots are always complex conjugate. So basically my system will be underdamped between 0.2 to 0.20. This will be the range of my k for the system to be underdamped. Now, what about overdamped? When my system will be overdamped? My system will be overdamped when my poles are negative and distinct. So system will be overdamped here, right? Poles are negative, real and distinct. So here, right, I have two poles at this location, then at this location, at this location, at this location, at this location. So here I have always negative and distinct poles. That means I will have always overdamped system. So in this is the range for which the system will be overdamped, right? So basically k lying between uh, k between -2 to -4 and k between -8 to -infinity. In this range system will be overdamped. What about critical damped? when is my system critical time? When the roots are negative, real and equal. So I see whenever these two branches meet, right, these two branches represent poles, right? This is one of the pole, this is the other pole. So whenever these two branches meet at this location, that means here, right, I have two poles at the same location. So breakaway point and breaking point are the locations when the system is critically damped. Okay, so k equals to 0.2, at k equals to 0.2 my system will be critically damped, at k equals to 20 my system will be critically damped. Breakaway and breaking both points my system will be critically damped, and rest so when will my system be uh, undamped? Whenever it will cross over the j omega axis. So at that point it will be undamped, but currently it is never crossing. So here I will not be able to find out the condition for undamped. So is there, like, what is the other way to solve without root locus? Of course, with equations. So this is my OLTF. Where is my OLTF? Where is my OLTF? Okay, I can just see with the pole zero diagram. My OLTF would be, give me 1 second. K upon s plus 8 divided by s plus 4 into s plus 2. Okay, yeah, that's all. K into s plus 8 plus s plus 2. So this is my pole zero diagram. Now now if I solve this further, yeah, so what is my characteristic equation? It is 1 plus g of s equal to 0. So this will be s square plus 6s plus 8 plus k into s plus 8k equals to 0. So s square plus s into 6 plus k plus 8 into 8k. Now for my system to be overdamped, right, basically what is my omega n? Omega n is under root 8 plus 8k, and my 2 zeta omega n for my system to be, let's take for the condition for my system to be underdamped, it has to be, so my zeta has to be less than 1. Basically 2 zeta omega n is this value, okay, 6 plus k, and my zeta must be less than 1. Okay, so your zeta must be less than 1. So here if I solve this, right, if I solve this will be 2 zeta omega n, zeta must be less than 1. So what is your zeta? Zeta is actually 6 plus k upon 2 into under root 8 plus 8k, correct? This must be less than 1 because this is your zeta. So we'll square both sides, assuming both are positive, everything is positive. So this will be 36 plus k square plus 12k plus 4 8 plus 8k. So this will be 36 plus k square. So let me write this properly. K square plus 12k minus 32k. So this will be minus 20k. Okay. Yeah. 12k minus 32. So this is also 32. Okay, 32, 32 minus 36, so plus 4 is less than 0. So again I can use the wavy curve method. So what is the wavy curve method? This will be so what are the locations, right? Factors basically. So poles are minus 20 plus minus b square minus 4ac, right? 4ac is minus 16 divided by 2a. So it is equals to 10 plus minus under root of 384. So 384 under root is actually 19.59. So yeah, it is almost 19.6, right? 19.6 upon 2. So this plus 10 upon 2, which is approximately 14.79. What will be the other root? So these are the roots of k. This is not the exact value. These are just the roots of k. So one root is this negative. If I choose another root, would be 19.6 plus 10 upon 2, that is minus 4.8. Okay, 14.8 and 4.8. So basically if I plot it, right, so one location, this is my real axis of k. One root it is at minus 4.8, another root is at positive, okay, sorry, minus 4.8 and plus 14.8. So of course whenever this, right, is greater, so this is my factor. So I hope you know Viveka method. I will not explain it over here. So whenever I am greater than my last root, it will be positive, okay, then it will be negative, and then it will be positive again. So basically I want to calculate the range for which this will be negative, right? Then only it will satisfy. So it is negative between when my k is minus 12.8 to, sorry, k is minus 4.8 to plus 14.8. So in this range k is, so this value is basically my system is under damped, okay, 14.8 to minus 4.8. Now of course you can ignore the negative solution, correct? Because k cannot be negative, k has to be positive. So the range for k for my system to be overdamped is 14.8 to 0.2. And here also we are getting something similar only, but I don't know, there is some approximation. This should not happen. I don't know what kind of approximation has happened, but it should exactly match actually. Okay, so there seems to be some approximation. I don't know what is the approximation, but that's fine. But I hope you can see, right, how difficult it is. It is very hectic task. But root locus, although it seems very difficult, plotting the root locus once you know how to plot is cakewalk. Okay, not that difficult. So let's try to plot the root locus for this particular OLTF. So yeah, let us start with, first of all, how many number of poles I have? 2. How many number of zeros? Sorry, how many number of poles I have? 4. How many number of zeros? 0. How many number of branches? 4. Maximum of pole and 0, 4. How many asymptotes? A number of asymptotes would be pole minus 0, that is 4. How many virtual zeros? 4. Number of asymptotes are nothing but the number of virtual zeros. So what is the angle of asymptote? So angle of asymptote formula is minus 180 2k plus 1 p minus z. K will go from 0, 1, 2 to the total number of p minus z minus 1 basically. P minus, so there will be 4 asymptotes, right? 4 asymptote. So k will go from 0, 1 to 3, that's all. 4 asymptote. What are the angles? So it will be p minus z is 4. So 180 by 4 is minus 45. So first will be minus 45, then I will have minus 135, then I will have minus 225, and then finally I will have minus, so yeah, 180 k to k plus 1. So when k is 3, this is 7 into 45. 7 into 45 would be 350. Yes, 350. That's all. So basically there is a break of 90. Okay, these are my angular asymptotes. Okay, we're done till this point. Let us now see, do I need any other information as well. So draw the pole 0 diagram. So one pole is at s equal to -1, -2, -3, -4. So of course, if I check along the real axis, if I check this point, right, on the right hand side, I don't have any polar 0. So it is even number of pole plus 0. So this will not lie on the root locus. If I check here, this region, on the right hand side, I always have a single pole. So it is odd. So this point will always lie on the root locus. There will be two branches here. Similarly, here if I check, right, I have even number. So this point will not lie. Here similarly, if I check, I have odd number. So this region will lie in the root locus. Okay. So that is it. That is it basically. So yeah. Now yep. Now what will happen? Now I know where are my asymptotes, right? Asymptotes, one asymptote is at -45. -45 is what? -45 is from the real axis. So you can choose plus also, right? It does not matter. Plus, minus, anything you can choose. Okay, I'll choose plus for my own convenience. Okay, for my own convenience, I'll choose plus, but you can choose minus as well. But if you are choosing plus here, everything will be plus. Okay, keep that in mind. So plus 45 meaning plus 45 on the real axis, so it will be here. One asymptote will be here. Basically, this angle, right, is plus 45. All right. Another asymptote is at plus 135. So plus 135 from the real axis, positive real axis. So one asymptote will be here. Okay, this angle would be, let me draw a different color. This angle would be 135. Similarly, you can plot it for the other ones as well. I will not I will explain everything. So yeah, these are my asymptotes. Okay, now next parameter, centroid. What will be the centroid? Centroid basically means whatever line I am joining all these asymptotes, right? Where are they meeting in the real axis? They will meet somewhere in the real axis. So the centroid would be, what was the formula? It was sum of the real part of the poles. What are the real part of the poles? So it is -4, -3, -2, -1, -0. I don't have any zero, right? So it is simply, there is no zero. So if there is no zero, right, you will put 0. That's all. If there is no zero, you will sum of the real part of the zeros, you will put 0. Similarly, if there is no pole, you will put sum of the real part of the poles to be equals to 0. That's all. This divided by number of poles minus number of zeros. This will be equals to yeah, -5, -9, -10, -10 divided by 2, that is -2.5. So basically, right, all these asymptotes will meet somewhere here actually. All these asymptotes will meet somewhere here. -2.5 is somewhere here. Okay. So -2.5 is somewhere here. So basically these asymptotes will meet at -2.5. Okay. Although my drawing is not proper, so basically I have to shift my asymptote. They will not actually be, they might not cross the j omega axis. Okay, might not cross the j omega axis. Might not. How can I say surely? I will explain. So these are my asymptotes. So what will happen basically? So your root locus will diverge and they will go towards the asymptotes. Okay, there are 4 asymptotes. So one root locus will diverge and they will go towards this asymptote. Other root locus will diverge, go towards this asymptote. Here also one root locus will diverge, go towards this asymptote, and here also one root locus will diverge and go towards this asymptote. Now how can you surely say that whether they will cross the j omega axis or they will not cross the j omega axis? How can you say that? So for that you can use Routh, okay, to find out the location of imaginary poles, to find out ROZ. That is one way. Okay, or you can take help of this particular thing, right? So you can put s equal to j omega and you can check whether it is satisfying or not. So there are multiple ways. So let us solve using both ways. Okay, because we have learned that in Routh. So yeah, what is my characteristics equation? It is 1 plus this, right? So your equation would be, this would be s square plus 3s plus 2 into s square plus 7s plus 12 equals to plus k equal to 0. Okay. Let me solve it. This will be s raised to power 4. I think we have solved something like this. Have I solved this? That is what I have solved this. Yeah. So we have already solved this. Let us not do the manual thing here, right? See here. So we have solved this. If you solve this, right? If you put s equal to j omega, if you put s equal to j omega, right? You will get, basically you will get proper solutions. Okay, you will get proper solutions. So your omega will come out to be √5. Okay, so you are getting proper solutions and omega is a real number. That means it will cross. So this root locus is actually wrong. Okay, so I will have to shift actually my stuff. I will have to shift my stuff. It will cross, basically it will cross the j omega axis. So how will the root locus look? The root locus will look something like this. Okay, and here also actually my angles were not proper at that point of time. So just give me 1 second. Now it is fine. Now the centroid also would be fine actually. Just even now the centroid is also fine. Just to make it roughly. Yep. Now it is fine. Okay. So this is basically my root locus. Always show the arrows direction. So this is, all these are k equals to infinity, k equals to infinity, and this is my k equals to infinity, k equals to infinity. These are my points of k equal to 0. So this part is clear now. Now what next? What next we have to do? Yeah, so we have got this, right? So that's all for this root locus. So you can also solve using Routh. So Routh also will help you actually. If you solve using Routh, you can also get the like the point, right? You got the omega. You can, by putting this s value, you can get the value of k as well, for which like it will cross. So this is actually called as the crossover point, right? What is the value of system parameter k when it is crossing the j omega axis? That is also a valid question that can be asked. Okay, either you can solve using Routh, you can solve using Routh, or you can solve using root locus, whichever way you find useful or helpful. Okay. Okay. A few. So are there any breakaway or breaking points? So if I solve, right, for breakaway and breaking points, if I solve, you will see that these are the solutions of my equation dk upon ds. It will be a third order equation because it was a quartic equation. So if I differentiate it, or one order will decrease. So that's why it will be a third order equation. So your break in and breakaway points, right, you will get this values. Okay. So these seems to be lying on the root locus, right? And yes, this is valid break in break. So there will be break in breakaway points, right? There will be some break in and breakaway points. Okay, there will be some break in and breakaway points because of course it will diverge here and here. So but you will say, sir, how will I solve a third order equation? The simple answer is you don't need to solve, because they will never ask you what is a breakaway or break in point in this particular root locus. Trust me, they will never ask you. Okay, or they will give you, right? Because of course, how are you expected to solve a third order equation? You're not expected to do that. So yep, don't worry about it. This was, I solved it using gate calculator, like not calculator. So this was using some other scientific calculator. So yeah, don't have to worry. But yeah, so you will get 3 solutions, out of which one of will be wrong, because s equal to minus 2.5 is not a valid point on the root locus, because this does not lie on the root locus. My on the real axis s is between -1 to 2, or it is between -3 to 4. As you can see, on the real axis it is between -1 to 2, or it is between -3 to 4 on the real axis. Otherwise it is not present on the real axis. So that's why you will neglect one solution, reject one solution, and you will take the other two solutions. That's how you plot the root locus. Okay, now let's solve the root locus for this. With this we will understand a very important thing regarding angle of departure and angle of arrival. Now this point is a point where I will say you have to remember, you have to put a bit of force on your brain. Till this point you did not have to put any force on your brain, trust me, right? Did you have to? No, right? But this point onwards you will have to put a bit of pressure on your brain. This angle of departure, angle of arrival, and your what do you call, complementary root locus. Okay, so listen to me very carefully here. So first of all, obviously let us locate the, okay, let me take a new page, that will be easier for us. Let us locate the pole zeros. So how many poles I have? I have total of 2 poles, and I have total of 1 0. What are the locations of pole? So pole location, open loop pole, right? These are open loop poles. So this will be minus b, that is 2 plus minus b square, that is 4 minus 4 AC, that is 8 upon 2a. So it is plus minus j2 upon 2, so it is 1 plus minus j. So I have complex conjugate pole. These are interesting. If you have complex conjugate poles, right, or if you have complex conjugate zeros, then you will have to do one additional step. That is what I will explain. So these are the locations of pole. My 0 is at s equals to minus 3. So my 0 is at s equal to minus 3. My poles are at 1 plus minus j. That's all, right? Now, how many branches? 2 branches. How many asymptotes? Number of asymptotes will be 1, pole minus 0. So angle of asymptote would be plus 180 into 2k plus 1, that is simply 0 in this case because I will have only one asymptote. So 1 divided by pole minus 0, that is 1. So I will have asymptote at theta equals to 180 degrees, right? Theta equals to 180 degrees, I will have asymptote. So if I plot, right, the poles, pole location will be minus b. Okay, this will be the pole location, right? So plus minus j1. So this is 1 plus j, 1 minus j, correct? And I have a 0 at is equal to minus 3. And I have a asymptote at 180. So basically I will have asymptote at 180 from the positive real axis. So basically this is my virtual 0. Now what will happen is, you know that root locus begins from pole, open loop poles. So it will begin from open loop pole, it will come here, correct? There will be 2 branches, correct? There will be 2 branches. Okay, this will go here, this will go here. That's it, your root locus is done. So you can compute, like this will be what you will have, only a single breaking point. You can compute a breaking point, right? So what will be my breaking point? We can calculate that. I can do that. So my k would be equals to, so 1 plus gs would be equal to 0. So k would be equals to minus of s square minus 2s plus 2 upon s plus 3. So if I solve this, right, if I differentiate, So what is the centroid location here? So I have only a single asymptote. Whenever you have single asymptote, you don't need to calculate centroid. So so differentiating this equation with respect to S. This will be equals to like negative sign will be there at the front. S plus 3 whole square, I don't care, right? I don't care about the denominator. All I care is about the numerator. So numerator, this will be 2s minus 2 into s plus 3 minus this chain rule I'm doing, and this into 1. Yeah. So this I will equate equal to 0. So basically this will be 2s square 6s minus 2s, that is 4s minus 6 minus s square minus 2, okay, equals to 0. So s square plus 6s minus, okay, this is minus 6 minus 2 minus 8 equal to 0. So this will be s equals to, so the real axis, of course, like although I have not explained it to you, but you can see, right, you can verify that on the right hand side, right, always I have a single like odd number of poles of 0. It does not matter, even if I have two poles here, right, it does not matter, because ultimately one pole is here, one pole is here, they will not change the outcome. What do I mean? Right, you know, root locus will be symmetrical about this. So if I have one pole here, one pole must be lying here, correct? Now even if I don't count the complex poles or zeros, it won't matter, because let's say I had 1 0 at the right hand side of this point, right? And of course if I have complex pole, they will be in pairs, so we'll add 2. So it will not change the outcome. Previously it was odd, now also it is odd, it will not change it. Previously, let's say if I did not have this 0, I had no 0 and these are my complex poles. So if I add 2, right, previously it was even, it is still even, right? So it won't matter if you count the complex conjugate poles or zeros or not, it does not matter, right? If you don't count these pairs, it won't matter, because ultimately if it is odd, it will still be odd, if it is even, it is still even. But just to have a good practice, include everything, okay? Because what you will do, I know you are smart, right? Maybe there are these poles, 4 poles, so you are very smart, you might choose in this only, this pole only, okay? You will do something, so don't do this, you will make some mistake. Choose everything, it will not change the outcome. Choose everything that is on the right hand side, choose everything. So I have 3 poles 0 on the right hand side, so of course all these points will be lying in the root locus, although I had not mentioned at the starting, but I hope like it is understood by you and you are doing your own calculations. So if I solve this, right, here minus b plus minus b square minus 4ac 32 upon 2a, so this will be 72 6 72, not 72, sorry, 66 68 68 under root and minus 6 upon 2, which is 1.123, and 66 under root minus 6 divided by 2, that is minus 7.06. okay, these are my two roots basically. Now here, right, what is valid, what is invalid? So of course s equal to plus 1.123, it will never lie, right, it will never lie in the root locus, so this point is invalid. This is a valid point, s equal to minus 7, this point is what, s equal to minus 3, correct? 0, I had a 0 at s equal to minus 3, so of course s equal to minus 7 is lying in the root locus, so this will be a my break in point. So yeah, now let's come to the interesting part, the new part, that is calculating the break in and the breakaway point. How will I calculate the break in and the breakaway point? So it's not, sorry, not the break in breakaway point. And so this, right, this root locus is leaving from the poles with some angle. On the real axis, we know it always leaves in the 180 degrees, correct? But what about here? In what angle is my root locus leaving? How do I calculate that? So this you have to remember, okay, this part you have to remember. This is called as the angle of departure. Why departure? Because it is departing from the pole. So for open loop poles, it is called as angle of departure. If I had complex open loop zeros, it would have been called angle of arrival, because the root locus would have arrived at the zero. As it is departing from the poles, it is called angle of departure. Angle of departure will be equals to, you can write plus minus 180, whatever you want to write. It will be better if you write just 180, okay? But minus 180 also will work, but right here plus 180, okay? Everything positive is good. Plus 180. Now you will add sum of all the angles of zeros contributed to this pole minus sum of all the angles of pole contributed to this pole. What do I mean by it? I will explain. That is why I am here. So if I have angle of departure, an angle of departure is calculated for pole, so you will write sum of theta p here. How to remember the formula? That is what I am explaining. As it is for departure, departure is for pole, so negative sign would be with pole. If it was angle of arrival, so same formula will be there for angle of arrival, same thing will be there 180, but this time it will be plus summation of theta p minus summation of theta z. So as it is arrival, it is for 0, hence 0 will be with the negative sign. That is how you remember the formula. Now I will come to the explanation. So here, what is the angle contributed by this pole on this pole? How do I calculate that? Okay, how do you calculate? So you sit in the pole. So basically, let's say I have a pole here, right? Let me keep to, I have a pole here in the bottom, like my phone, this location, and I have another pole here, right? These two poles are at top of each other. Okay, this phone is connected to charger. Let me just, okay, let me use some lightweight stuff, correct? Just give me 1 second. So I have a pole here and I have another pole at the top. So how do I explain this? So this kind of thing, right? Yeah, this kind of thing, right? So I have a pole just here at the center, and just at the top of it I have another pole, right? Because it is symmetrical. Similarly, you can see I have one pole here, another pole here. So what is the angle if I sit in this phone and observe this point, the top point? How much does my head needs to move to view the point? So if that point is directly above me, right? I'm sitting here, right? I'm sitting here. This is me. I'm sitting here. Okay. So how much do I need to move my head from the? So I'm always looking in the forward direction. So I'm looking in this direction, right? In this direction. How much do I need to move my head so that I can observe this particular pole? Because I want to calculate the angle of departure for this pole. So that's why I have to observe the pole. So if I'm lying here, how much do I have to move? I have to move how much? Plus 90, right? Plus 90, right? Because you are seeing in the forward direction, you have to move plus 90. Okay. So I have to move plus 90. So the angle contributed by this pole on this pole is plus 90. So this will be plus 90. Do I have any other poles? No, I don't have any other poles. So that's it. If I had any other poles, I would have added the things for as well. Let's say if I had a pole here, right? So how much does this pole need to move its head? So if I'm sitting here, correct, how much, so I'm looking in this forward direction, how much do I need to move so that I can look in the pole, I can see the pole, right? How much is it? So for that you need to calculate. So it is a triangle, right? This will be theta, this will be 180 minus theta, this will be some x, this will be some y. So now you are very smart, you guys are very smart. You will calculate theta from tan theta, whatever formula you will use, then you will calculate 180 minus theta, and that will be your answer. Okay, that's how you calculate the angle of like theta p. Similarly, theta z also is same, carbon copy ditto. So if I am sitting here, right, how much my head is looking in the forward direction, how much do I need to, how much does my head needs to move so that I can observe this? So again, we will calculate the x distance. What is the x distance? The x distance is, this is -3, right? What is the x coordinate here? 1. So this overall distance would be 4. So the x coordinate distance is 4. That's all. What is the y coordinate distance? Y coordinate distance is, so I am lying in the where y equal to 0 and this point is y equals to 1, right? This point is y equals to 1 basically. So this y coordinate would be 1. The distance from here to here is 1. Now you are very smart, above smarto, you can calculate theta z. What will be theta z here? Theta z would be tan inverse 1 upon 4. Okay, am I correct? Yeah, tan inverse 1 upon 4, that would be your theta z. Okay, so theta z is tan inverse 1 upon 4, that is approximately, if I calculate this value, just 1 second. 1 upon 4 tan inverse. Okay, hold on a second. 14, approximately 14 degrees, right? So tan inverse 1 upon 4. So this is my theta z, right? So I only have a single 0, so I don't need to include any other zeros. So you don't need to include virtual zeros. Okay, no need to include virtual zeros. Great. Same thing you can apply here as well, right? How is it -90 actually? So you see, do I have to move anywhere in the x coordinate? No. So my x is 0, correct? What is the y distance? Y is, this is how much? 2. So tan inverse 2 upon 0, tan inverse infinity is 90. That's why it came 90. So if you have enjoyed the explanation of angle of departure and angle of arrival, hit the like, put the comment down below. Okay. So yeah, like just as a good appreciation that yes, you are listening, right? You are listening, you're understanding the things. Okay, trust me. Like I know this, right? You will never study this kind of things anywhere else. I know this because I myself have studied, right? During my gate days, right? I myself have studied, so I know these things. So if you are understanding the concept, hit a like and comment. Great. So I got my 14 degrees. So what will be my angle of departure? Angle of departure would be 180 plus 14 minus 90, which is 104 degrees. From what? From the positive x-axis. Basically, if I am sitting here, right? So I am looking in the positive x-axis. So my angle of departure will be plus 104. Okay. So actually, yeah, angle of departure will be plus 104. So 104 will be lying somewhere around here, right? This part is 90, right? So 104 will be lying actually somewhere here. This will be my theta departure. So actually root locus will be something like this. That's why you should plot your root locus properly. Your root locus will be like this. Now your root locus is more exact. Okay, here also as it is symmetrical, so if you have calculated the angle of departure here, right, the other one will be just negative, opposite. Okay, because it is symmetrical. So you just calculate the angle of departure for one of the poles, you can easily calculate the angle of departure for other pole. Why? So here, right, you will see that it is symmetrical, right? So if this is theta d, okay, so as it has to be symmetrical, it has to start from here. So this much angle is theta d, right? What is this? This is the angle, this much angle. So this much angle is actually theta d. But whenever we are computing angle of departure for a particular pole, we always compute with respect to the positive x-axis. So if this is theta d, because this is theta d and it has to be symmetrical about the real axis, hence what will be the angle of departure for this pole P2? It will be 360 minus theta d. Okay, I hope you have got this point. Sorry, no, not 360. Sorry, the angle of departure here. Yeah, 360 minus theta d. Yeah, that is correct. You can write angle of departure here will be 360 minus theta t, or you can say angle of departure will be minus of theta t of P1. Whatever theta t you have calculated, let's say this is theta t P1. So here angle of departure will be minus of theta t P1, because here I am measuring, I am going in the clockwise direction, right? As it is symmetrical, it will be minus of theta t. So if you know the angle of departure of one pole, you know the angle of departure of other pole as well. Just you have to add a negative sign. Why? Because it is symmetrical. That is explained to you, right? So these are the things. That's it. And your root locus is almost done. Few small topics are left that we will learn. That's it. So if you plot, right? I think in the actual computer as well, MATLAB as well, we have plotted the root locus. Where is it? Here. Yeah. If you see, yeah, you can see like this is more prominent, right? You can see the angle of departure like this. So I've initially drawn my root locus like this, but that is incorrect. This is more accurate, right? So this represents the angle of departure. Okay, and from here you can deduce like when my system will be stable, what will happen, critical damp, over damp, those things will be there. You can understand that. Okay, so this was about the conventional root locus. Now few questions we will do, actually 1-2 questions regarding one small concept which I missed initially. Okay, so for the system shown below, they are telling me that this lies on the root locus, then the value of k would be. So if a point is lying on the root locus and nothing is mentioned, so k, it must satisfy the characteristics equation, that is 1 plus OLTF. OLTF is what? G of s upon 1 plus G of s into h, because it is not a unity feedback system. It has to satisfy this particular equation, right? Sorry, this has to satisfy basically this equation, 1 plus G of s equal to 0, characteristics equation, the denominator, basically the denominator. So this would be 1 plus k into s plus 3 upon s plus 2 into 10, okay, equals to 0. Now if it is satisfying the root locus, they are telling me that this lies on the root locus. If it lies on the root locus, then that means it has to satisfy the characteristics equation. So I will put the value of s. Just put the value of s. If I put the value of s, this would be 1 k minus 2.5 plus 3 upon s divided by, so minus 2.5, so this will be minus 0.5 into 10 equal to 0. So from here you can easily calculate what is the value of k. This will be 0.5 minus 1, so minus 10k. So k is equals to 1 by 10, which is coming out to 0.1, which is a valid value for k. K has to be positive, right? Sorry. Okay, that is interesting. It is coming out to be 3. How is it coming out to 0.3? Sorry, minus 2.75. Sorry, minus 2.75. They're telling me minus 2.75. So minus 2.75 is this. This would be 0.75. This will be 0.25. Okay, 0.25 meaning this is 1 by 3. 1 by 3, yes. 1 by 3, yeah. So this will be 3 by 10. So 0.3, which is valid, right? K has to be positive. And I'm getting k as positive. So this, whatever they told me that s lies in the root locus, it is valid. K has to be positive and real. So yeah, it is a valid. So that's how you can find the value of k. That is one question. Another question is there. Another type of question is there, that if the open loop transfer function is given, the value of gain k, which is positive, for which this lies on the root locus. So if it is a NAT type question, anyways, you know that if they are asking you numerical answer, right, it will lie. This point will lie in the root locus. But sometimes there will be MCQ, right? And sometimes the point they will give you that may not lie on the root locus. So the easiest way to find out the value of k is simply put on this equation 1 plus, this is a negative unity feedback system, GH equal to 0, and you check whether it lies on, like you simply put s equals to minus 1 plus j2 and after putting this value, if you get k as a positive real number, that means this actually lies on the root locus, and whatever value you have got is the correct value. But after putting this value, if you get a negative value or any complex value of k, right, complex or a negative value, that means this point actually does not lie on the root locus. Okay, I can show you example as well. I'll show you example, but sometimes this calculation is huge, I will tell you. So let's do this, right? Let's put this value in the equation. If I put the value in the equation, what will happen? 1 plus k into s, that is minus 1 plus j2 plus 4 plus 8. This is minus 1 plus j2 whole square minus 9. So this, right, if I solve this, okay, yep, this will be so this is a bit tedious, right, bit hectic. So that's why sometimes we avoid doing this, right? So basically, right, if I solve for k, right, k has to be a okay. So if I want to check whether this point lies on the root locus or not, what do I have to do? I have to simply do one thing, right? So this, right, my g of s, this will satisfy the root locus. So g of s will be equals to minus 1. So there are two things, like this is the actual derivation of root locus that we skipped initially. So the magnitude of g of s has to be 1, or angle of g of s has to be, like these two conditions needs to be satisfied. Both of these, right, has to be plus minus 180, right? So if you have to, like you already have been given a NAT, right, and you know this point lies on the root locus, simply go by the magnitude condition, because for this point to lie in the root locus, both of these conditions needs to be satisfied, but you don't have enough time, right? So you can ignore checking this part. You can only make magnitude equal to 0, and from that you will be able to find out the value of k. How will I will explain. But if there is options and one of the options tells that this point, given point, does not lie in the root locus, then you have to check both the conditions, check both the magnitude and the angle, right? So let's actually verify with the angle condition. So if I was in the exam, I will only do the magnitude condition, because with the magnitude condition I will directly be able to find out the value of k, and I know this point lies on the root locus. Why? Because this is a NAT type question. Okay, but here we are solving the question, so like we have enough time. So I will check the angle condition. So if I check the angle condition, correct, so what is g of s? G of s is this. So angle of g of s, so it will be so the numerator is minus 1 j2 minus 1 j4 divided by minus 1 plus j2 plus 8 into s square, right? S square is this. So actually I have to square this, unfortunately. So this will be 1 minus 4 minus j4 minus 9. So this will be 3 plus j2 this will be 7 plus j2, this will be minus okay, minus 9, minus 8, minus 12, minus j4. Okay, so what is the angle contributed by the 0? It would be tan inverse 2 by 3 minus the angle contributed by the pole tan inverse 2 by 7, and of course both of these are negative. If both of these are negative, that means this will be okay. Both of these are negative, so they are lying in the third quadrant, so this will be 180 plus theta. 180 plus theta, so 180 plus tan inverse. I will not explain how to calculate angles, right? This you know before. Okay, so if I solve this particular equation, let me solve this equation. So this would be 2 by 3 tan inverse, hold on a second, 2 divided by 3 tan inverse, and then minus 2 by 7 tan inverse, then minus 180 plus theta, right? Yeah, 180 plus theta, then minus 4 by 12 tan inverse. So it exactly comes out to be exactly minus 180, which is actually satisfying my angle condition. So that means this point lies in the root locus, although we already knew, right? We knew because this was an 80 type, but that's how you verify. So in the question, if a MCQ is there, so you have to verify whether this complex point lies in the root locus or not. How? You will use the angle condition. Okay, because if you plot the root locus, right, it is very difficult for you to check whether a complex point lies on the root locus or not. It is very simple to check for the real point. That is very simple, right? Just count the odd number of poles and zeros. But here, right, it is not that easy to verify. So you have to actually know this trick, right? Finding out the angle condition or the magnitude condition. Now in this case, if you have to find out the value of k, like first thing is you can directly put the value of s, right? If the s is real, right, then you directly put the value of s and directly you can find out the value of k directly. But if s is complex, it is very tedious. If you put complex numbers here, it will be very tedious for you. What you will do? You will use the magnitude condition. So magnitude has to be 1, right? So if I calculate the magnitude of this function, right? So this is my function. Just have to multiply k, because k does not provide any phase shift because it is positive number. It will not provide any phase shift. So magnitude of this particular function would be 3 square plus 2 square under root upon 7 square plus 2 square under root 12 square plus 4 square under root. So this will be equals to also k is there, right? K will be there, and this has to be equals to 1. Magnitude condition needs to be satisfied if this point lies on the root locus. So from this I can easily calculate the value of k. This would be 7 square plus 2 square into 12 square plus 4 square divided by 3 square plus 2 square whole under root. Yes, so k value comes out to be 25.25. Is it correct? Yes, 25.54. Yeah, k will, after solving this, k will come out to 25.54. That is what I have done here as well. I have used magnitude condition. So magnitude condition will actually help you to find out the value of k. Correct. Angle condition just tells you whether that particular point lies on the root locus or not, because what happens is actually k goes away, right? Whenever you calculate the angle, k is not there in the calculations. I hope you get the point. Now let's come to the next part, that is complementary root locus. Till this point we have always discussed that k will always be positive. Okay, so now what can happen if k is positive? What if k is positive and you have a positive feedback? We have discussed for negative feedback. Whatever has been discussed, everything, whatever rules we have discussed, all those rules are for negative feedback. If I change this, right, then the angle condition changes, correct? What will happen to the angle condition? So now your characteristics equation, it will not be 1 plus gh, it will be 1 minus gh, right? For positive feedback, you remember the denominator of the CLTF is 1 minus gh. Here h is 1, so 1 minus gh equal to 1. So your g of s is equals to 1. So your angle condition becomes, your magnitude condition is same, right? That is 1. Your angle condition has changed. It is 180. So it is 0 degree now. 0 or 360. You can say it is 360 degrees. Okay. So your angle condition has changed. So so basically all the rules are derived from this condition only. Okay, trust me, all the rules are derived from this condition only. So whichever conditions use this particular angle condition, right? All those rules will change now. And don't worry, like it has very less probability of getting asked, but you should know something like this exists. And if you ever get stuck in the exam, go by basics. Check, put that particular point in the characteristics equation and see whether that point lies in the root locus or not. Then you will be able to figure out the rules. Okay, just put any real value of s, negative real value of s, and check whether it is lying on the root locus by solving this characteristics equation. If it is satisfying, then of course whatever rules you are thinking of, those rules are correct. So that's how you can verify. Okay, now this is also called as the inverse root locus, where my k is positive system parameter, but my feedback has changed. It has changed to positive feedback. There can be other cases as well, right? If I have negative feedback, but what if the parameter k value is negative? It is negative, then it is called as complementary root locus. Okay, so don't worry about the names, just understand what are the cases, conditions. So if k becomes negative, right, then also your angle condition will change here, right? Your angle condition will change. Why? Because what is happening, your characteristics equation is same. It is k into g of s equal, here also it was k into, basically this was k, right? Now as k does not provide any phase shift, okay, as k does not provide any phase shift, actually this would be k into magnitude of k into gs, and this will be angle of k into gs, right? And as k is positive, so k does not provide any phase shift, so I can directly write this as angle of gs only, right? Directly write angle of gs. But in this case, if k is negative, right? If k is negative, then k will provide a phase shift. How? So let's say my g of s is simply 1 by s plus 1. Okay, g of s is 1 by s plus 1, and let's assume for k equals to 2 and for k equals to minus 2. What is the phase provided at s equals to minus 1, j1, minus j1? Okay, what is the phase provided at s equal to minus j1, right? Or let's say at s equal to plus j1 only. So the phase provided, right, of k into gs, right? Because ultimately you have to satisfy this equation, 1 plus k into gs, not only gs, because k is also there, correct? So what is the phase provided by k into gs? When my k is positive 2, so what will be k into gs? K into gs would be angle of 2 by s plus 1 at s equal to j. So this will be actually basically minus 45 degrees. What will happen here? This will be angle of minus 2 by s plus 1 at s equal to j. Okay, now the thing is that what is the angle? I hope you understand angle, right? If this is negative, this negative actually provides a phase shift of 180 or plus minus 180, whatever you want to say. And additionally, I have another phase shift of 45, minus 45 from the denominator. So overall phase shift becomes minus 225 degrees. Okay, so it becomes minus 225 degrees. So one thing I'm just thinking whether I should write minus 180 or it won't matter actually. It won't matter, yeah, it won't matter. So overall I'm getting a phase shift of minus 225. Okay, so you see, right, the angles are different. So actually if k is negative, then the angle condition will change. That's why this here the angle condition would be same as this condition. although it is negative feedback, but the angle condition, because K additionally provides another 180 degree of phase shift, because K itself is negative, that's why the angle condition changes. But in this case, right, where I have positive feedback, but K is negative. If K is negative, positive feedback does not provide any angle condition, but K already provides a, because it is negative, 180 degree. So this case is same as this case. So you don't have to worry about this case, right? Two cases are gone. Only you have to worry about this case and this case. I hope you understood what are these cases and what things will change. So what things will change? As the angle condition has changed, few things will change. I will explain one by one. So the open loop poles, locating the open loop poles and zeros, those that method will be same. Root locus on the real axis, identifying location will be different. Now what will happen for complementary root locus? If let's say I have a pole 0 here, right? For complementary root locus, you will not find odd number of pole 0. You will find even number of pole 0. Why? Because the angle condition has changed. That's why. So for complementary root locus, if it was normal root locus, what would have been your root locus? This would have been your root locus, right? Now if it is complementary root locus, your root loci will be this. So you will start, all those points on the real axis will lie on root locus if I have even number of poles plus 0. So here, right, in this region, always if I see on the right hand side of my point, I have odd number of poles plus 0. So this is actually not a valid point in the complementary root locus. This is a valid point in the complementary root locus, because all points on the right hand side, I don't see any pole of 0, it is 0, and 0 is an even number. So all these points will actually lie on the root locus. Okay. Here as well, if I see, all these points are lying on the root locus. Okay. All these points will lie on the root locus. Now, okay, few things. Okay. Okay, that this has changed. Now let us discuss about asymptotes. So asymptote condition also will change now. It indicates the trace of closed loop poles as my test point tends to infinity. So asymptote condition also will change. Now previously it was 180, right? The formula. Now it has changed to 360. K is same. K is basically p minus z minus 1, like till the point that will go. So in this case, what is p minus z? It is 0. Correct? So angle of asymptote is 0 degrees. Okay. Okay, it is 0 degrees. So here we got stuck, right? So whenever you are stuck, just write down the characteristics equation. That's it. So if I simply assume a characteristics equation here, right? Just give me a second. If I simply assume a characteristic equation, let's say 1 minus, as it is a complementary root locus, s plus 3 by s plus 2. Okay, this is exactly copying this thing, equal to 0. If I solve for s, right, you will see, if I solve for k, because if I solve for s, this will be s plus 2 equals to k into s plus 3k. Correct? If I make this on the right hand side, so this will be s equals to 3k minus 2 upon 1 minus k. So actually at k equals to 1, right, this equation will not be valid. S will be infinity. K equals to 1. S will be infinity. So I cannot put k equals to 1. So there will be actually a break point at k equals to 1. Okay. So this root locus, there will be somewhere, there will be some break. Okay. Somewhere there will be a break point. This root locus will not be proper. So in complementary root locus, we get this kind of problems. So don't worry. Don't need to remember, like remember few things, whatever you are able to remember. But if you are ever in confusion, just put that in the formula. Put in the characteristic equation and then solve. Don't worry. Okay. Don't need to worry. So these are few rules basically. You don't have to worry. So one more thing is there. So angle of arrival and angle of departure also will change. For whichever condition had angle, right? Whichever had angle, all those things will change from 180 to 360. That's all. Angle of asymptote will change. Angle of arrival, angle of departure, these things will change. Okay, and this condition will change, right? Odd number, even number of poles. That's all. I think these are the things. Number of branches will not change. Number of asymptotes will not change. Those things will not change. Yep. Actually, here I don't have any asymptote, right? So will not consider any asymptote. So yeah, let's plot a very basic function, and with this we will wrap up the complementary root locus, and like further we will solve your gate PYQs. Correct. So I have this particular question. Now we have to identify the root locus. The first step is always 2. How many number of poles I have? 2. How many number of zeros I have? 1. How many branches I will have? 2. What are the locations of pole? Minus 2, minus 2, minus 4, minus 8. Okay, so that's all. Now let us solve this, right? So this is complementary root locus. Okay, complementary. So I have to check for even number of poles and zeros. So here I see I have even number of poles and zeros. So all this will be lying in the root locus. So one of the branches will connect these two, this pole and zero combination. Okay, and there will be one more branch. So here I see on the right hand side I don't have any poles or zeros. So this is 0, right? So this will be lying on the root locus. Here on the right hand side I see I have odd number of poles and zeros. So this will not lie in the root locus. So this will be the other branch. This will be the other branch, and here I will have asymptote, because how many asymptote I have? Pole minus 0, that is 1. What is the angle of asymptote? It is 360, not 180, into 2k plus 1, which is 1 basically, upon pole minus 0, that is 1. So it is 360, which is same as 0 degree, correct? So at 0 degree I do have asymptote that can be verified here as well, correct? So that's it. That's it. This is my root locus. Okay, now do I have any break in or breakaway points? Like we can so yeah, that's all basically, that's it, right? So do you remember what was the root locus for your normal system? For your normal system, which was the root locus? So what was the root locus for negative feedback? Normal root locus, right? The normal root locus would have been, if I have pole 0 here, this is my pole 0, minus 4, minus 2, then again I will have one asymptote. What will be the angle of asymptote? Minus 180, right? The angle of asymptote will be minus 180, so one of the asymptote will be lying here actually, minus 180. So there will be two branches. One will start like from here, other one will start from here. Both of them of course will start from poles. So they will break away together, and then they will again join here. Okay, so this was the normal root locus, right? And this is the complementary root locus. So you see, like there can be a common point between, like there can be point of common region, right, in the normal root locus as well as the complementary. It's not like complementary root locus will be exact complement of normal root locus. No, not like that. Okay, there can be common regions. So you can, if you see that okay, sorry, it is actually exact complement. Yeah, it is actually exact complement. That's interesting. So it is actually exact complement, but I am not sure. I have to check whether it will be always like this, that here if you see, right, it is the complementary root locus is lying between minus 8 to minus 4. Here there is no valid point between minus 4 to minus 8, right? This is minus 8. So actually it will be exactly complement, but I am not sure whether it will always work. I think it will. That is what my gut feeling says me, but I have to further validate. But don't need to worry. So just that's how you draw the complementary root locus. That's all. So there are more things, like what is the crossover point? So you are seeing that s equal to 0 is a valid point on the root locus. So what is the value of k when s is equals to 0? So if it's a complementary root locus, right, then k is positive, it is a positive feedback. So what is the characteristics equation? It is s plus 8 upon s plus 2 upon s plus 4, right? So let us see if actually s equal to 0 lies on the complementary root locus or not. If I put s equal to 0, this will be 8k upon 2 into 4, that is 8. 1 minus this, that is equals to 0. So from this, my k would be equals to 1, and that is correct because my k here is supposed to be positive and real. So this point actually lies in the root locus. That is correct, right? So this point will be k equals to 1. That's it. Okay. If here s equal to 0, does it lie in the root locus? You can use the characteristic equation. It is 1 plus, because it is a negative feedback, right? It is not positive. K into s plus 8 upon s plus 2 s plus 4. So basically, right, if you put k equal to 0, s equal to 0, equal to 0, this equal to 0, so you will see that k is coming out to be -1. That is not valid because k has to be positive, right? So that's why this point s equal to 0 is an invalid point on the root locus. That's how you can verify. So that's it basically. That's like there are a few more parameters. You can pause the video, you can check whether I will have a break-in point or break-away point. So if you compute like the condition for break-in and break-away point, those remain same. How to calculate break-in and break-away point? That step is carbon copy same. There is no difference. Okay. Just maybe your break-in and break-away point will be swapped, right? No, they will also not be swapped. Sorry, what am I telling? They will they may be swapped. They may be swapped. Breakaway and breaking point, the condition may be swapped, but like that is how you can check, right? The how to check the breaking point or breakaway point. First you do this, find out the derivative of k with respect to s. You find out the points and check whether these points are lying in the root locus or not, right? That's how you can simply check. So you will see that this is k equals to infinity, this is k equal to 0. You will see that whatever points you are getting, right, those are not actually lying in the root locus, invalid. So those will be invalid breaking points. Okay, so that's how you can verify and confirm. So I think that's pretty much it. So I have told you everything, right? How is, so if nothing is mentioned, you will always use the complementary root locus, right? If nothing is mentioned, you will always use the complementary root locus. Okay, so these are the 4 cases for which we have discussed. So just remember this one, and opposite how to remember, that also I have explained. Now one more short thing is there. Okay, this find out the intersection of asymptote on the real axis of the following voltage. It is pretty simple, right? How to find out the intersection of asymptote on the real axis. Now just one small thing, right? So here, right, what is the formula for intersection of asymptotes on the real axis? It is basically summation of real parts of all the poles minus summation of real parts of all the zeros divided by poles minus 0. That's all. Okay, divided by poles minus 0. Now what you can do, these, like you will get complex conjugate roots, right? So this I will get a root at -1 plus minus j, I think, and here also I will get some root, I don't exactly remember. But the interesting part is, for calculating the intersection of asymptote, you don't need to calculate where does my root lie. You just need to calculate the sum of the roots. If I calculate sum of complex conjugate roots, the imaginary part is gone, the real part is doubled. If I add the 2 roots, it will be -2, right? Imaginary part will be cancelled. So the point that I am making for this question is, you don't need to calculate the location of roots. Okay, you just need to calculate the coefficient of the s raised to power 1 term for a second order equation, because coefficient of s raised to power 1 term tells you the sum of the okay, hold on, I think this would be sorry, this right equation, solution of this equation is this, right? Sorry, so this, roots will not be this, actually the roots would be, actually, yeah, for this the roots will be this, for this will be the roots, basically whatever I discussed, right? That was for this -1 plus minus j, that was the roots of this equation, s square plus 2s plus 2. So basically, right, do you remember what this coefficient tells us? This coefficient tells me the negative of sum of roots. I hope we remember, right? For a quadratic equation, this coefficient tells me the negative of sum of roots. So actually, to calculate the negative, so I just need to calculate the sum of roots of poles. So if I just add a negative sign and put this coefficient here, will you be angry? No, right? Because ultimately the imaginary terms will be cancelled. You can see, right? These are my poles. If I add them twice, ultimately the imaginary term will be cancelled. Only -2 will be there. Similarly here as well, right? Only -1 will be there. Okay. negative of this. So minus 1, minus 2, minus, do I have any zeros? No. If you don't have any zeros, we'll simply do 0 upon number of poles minus number of zeros. So number of poles is 2, number of zeros, sorry, number of poles is 4 actually. 4 poles, right? It is a, like I have 2 poles here, 2 poles here. So number of poles is 4 minus 0. This would be equals to minus 3 by 4. That's all. So minus 3 by 4 would be your answer. Okay, this was one trick that I wanted to say. And last one thing is left. Find the location. Okay, find the location of the complex conjugate roots for the following relative. Sorry, this is not the right. Find the location of complex conjugate roots. So basically, not location. Actually, they're asking us find the loci. What will be the behavior shape? Will it be a circle, parabola, semicircle? Actually, complex conjugate root, right? If I have only a single zero like this, it will always be a circle. There is a derivation. Here is a derivation, right? Proof is there. You can pause the video. I can see the proof on your own. No problems. But ultimate conclusion would be the center of the circle would be sum of the breaking point plus breakaway point by 2. This also you don't need to remember. Don't worry. This you don't need to remember. But it is a formula that is derived from here. I have derived it. Okay, don't worry. But the center will always be the lying on the not on the leftmost, not on the rightmost zero. Previously I told you rightmost zero, that is wrong. Center of the circle will always lie on the leftmost zero. What is the leftmost zero? Minus 4. So I will have a circle if I plot the root loci whose center will be at minus 4. How do I calculate the radius? It's very simple, right? You will compute the break in point and breakaway point, right? And this will be just at the center. So the distance from the zero, from the leftmost zero to the break-in point or breakaway point will be the basically my radius. That's all. That would be my radius. That's all, right? That's how you can calculate the radius, right? Right? Why will it be on the leftmost zero? There is a proof. We are not getting into the proof. Now to remember these formulas, just calculate the break-in or breakaway point, and you know where the center will lie. It will lie at the 0. Okay, and that's it. Okay, and you can also like if you solve my solutions, right, in somewhere in the questions I will solve, or if it is in the question I will tell you that automatically you will understand. Basically, right, whenever you will compute your breakaway point or breaking point, it will come out like in this case it will be a second order equation, right? You will differentiate k tk upon ts, right? So it will come out as a second order equation, right? S raised to s square plus some coefficient s plus some coefficient s raised to power 0, right, equal to 0. So you will get roots, okay, and your roots will be some minus b plus minus b square minus 4ac upon 2a. Now the interesting fact would be basically, right, this distance, right, minus b upon 2a, this will be your center actually, because what is the property of a center? The property of a center is the distance from the center to the perimeter of the circle will be same on one side and on the other side. Same thing, right? What is the radius? The radius would be b square minus 4ac upon 2a. So this actually is the radius. If you see from minus b, I am going left. From minus b, I am going left this much, and on the right also I am going this much. So the distance from the center has to be same. So actually this point is actually the center. So minus b upon 2a is actually center, which is supposed to be the rightmost zero. Luckily, it is supposed to be the rightmost zero. In the derivation, it comes out to be like this. Okay, the same thing I have done here, right? Whenever you solve a second order equation, you will get two solutions. Basically, from the center, it will be this will be the center basically minus b upon 2a, and the other 2 points will be the radius. So basically, this will be my radius b square minus 4ac under root by 2a. This will be my radius. Okay. Don't worry if you did not understand. Just understand this, and like from the equation you can understand. You can understand, right? Basically, from the center, I should have same distance. So if this is my center, right, then if I add under root b square minus 4ac, I will move on this on the right hand side. If I subtract b square minus 4ac, I will move along this side. I am subtracting and adding same distance. So this distance and this distance is same. That means this has to be the center. That's how I can say. Okay. So with that, we are done with the with the theory. Now we will start with the questions. This is the first question. The characteristics equation is shown. In the root locus, k is varied from 0 to infinity. the breakaway or breaking points lie within what. So you don't need to calculate the breakaway breaking points. You simply need to plot the root locus. That's it, right? And by default, you will assume negative feedback system. So if something like this is given, right, then you have to convert it into your proper format. So what is your proper format? Your proper format would be 1 plus k g of s equal to 0. This is your proper format. Then only you will be able to plot a root locus. So let us convert it into proper format. So this will be s cube plus 3s square plus 2s plus k into s. I will just take the k terms together, s plus 3, that's all, equal to 0. So from this I get the information regarding my open loop poles and open loop zeros. So I see that I have a open loop 0 here and I have a open loop pole here. This will be okay. Yeah, that's all. So if I take this common, right, this will be converted into this, right? So this I can write in a more neat manner. This will be square, this will be 1, this will be 0, and I can take s common. Okay, so what is the location of this will be s plus 1 into s plus 2, correct? Yes. Yep, great. So I now finally I can draw the root locus. So you have to convert your characteristics equation into proper format. So now I have a pole at s equal to 0, I have a pole at s equal to -1, I have a pole at s equal to -2, I have a 0 at s equal to -3. So how many asymptotes I will have? I will have actually 2 asymptote. What will be the angle of asymptote? Angle of asymptote, right? I will have 2 asymptote because pole -0. I will have 3 branches, right? Angle of asymptote, right? So it will be 180 by p minus z, that is by 2. So one will be 90, another one will be 19 to 3, right? 270. So one asymptote will be here, one asymptote will be here actually. That is interesting. So basically root locus will be somewhat like this, correct? So one asymptote will go here, one will go here. So I'm just doing this roughly. So this will be my rough root locus, correct? So either it, like, I don't know whether it will cross j omega axis or it will not cross. I don't know. How can I verify? So for this, right, you can actually calculate the centroid. Wherever these asymptotes, the asymptotes meet. So what is the centroid? Centroid would be sum of the poles. What is the pole? Sum of the pole location. So -1, 0, -2. So which is -3. Minus sum of the zeros, which is -3, upon pole -0, which is 2. So it is coming out to be 0 actually. So actually my asymptotes, their centroid, basically their line joining the asymptotes, right, is exactly at 0. So they will never actually, almost they will never touch they never cross the j omega axis. That's how you can verify. Now one more thing I forgot to tell you, your break away point will always lie for a normal root locus between two poles, between two consecutive poles. Your break in point will always lie between two zeros. This will always be valid. Previously also you can cross verify and check the video. Your break in point were always lying because it has to break in and then go into the root locus. That's why it has to lie between two zeros or two poles. Here I see I have two poles. So break away point has to lie between these two poles for a normal root locus. So your breakaway point will lie between -1 to 0. You don't need to solve it further. Of course you can calculate, but you don't need to solve it. Your breakaway point will be lying between -1 to 0. So option A will be the correct answer for the question. Let's solve the next question. The loop transfer function of a negative feedback k greater than 0, the value of k at the breakaway point of the root locus is. What is the value of k at the breakaway point? Very simple. So what do you have to do? Simply right? uh, Either you can directly, so let us first of all plot the root locus, right, because it will help us in uh, discarding the invalid points, invalid breakpoints. So s equal to 0 I have a pole, s equal to -2 I have a pole, s equal to -6 I have a pole, and yep, there will be a breakaway between two consecutive poles, right? There will be three asymptotes. So one asymptote will be actually here, one asymptote. So yeah, let me calculate. So it will be, angle of asymptote would be 180 by pole minus 0, so 3. So one of the angle will be 60, other will be actually 3 into this 180, other will be 300. So basically 60 would be, again, what is the centroid? Centroid is actually -2 -6 -0 upon 3, which is actually -8 upon 3, correct? So which is never in like, which is in the negative side only, so it will actually never cross the j omega axis. So this will be my asymptotes basically, okay, never cross the j omega axis. Roughly I am drawing, not exactly, okay. That's all, that's all, right? Now yep, now this will be 0. So my break-in point has to lie, sorry, breakaway point has to lie between -2 to 0. My breakaway point has to lie between -2 to 0. So let us now solve, right? It is a negative feedback system, unity negative feedback system, nothing is mentioned. You will assume unity negative feedback system. So you will do 1 plus k, so let me solve it here only. 1 plus k upon s into s plus 2 into s plus 6 equals to 0. So this would be k into, so okay, we have to differentiate this, right? K is equals to s into s square plus 8s plus 12 minus, or it is equals to minus s cube minus 8s square minus 12s. Yep. So now I have to differentiate this. So this will be minus 3s square minus 16s minus 12. This is equals to 0. So s square plus 16 by 3s plus 4 equals to 0. So I will get two solutions, b square minus b plus minus b square minus 4ac. Let me solve this, right? Let me solve this. So b square minus 4ac, this would be 16 divided by 3 whole square minus 16 whole under root 3.5. So plus minus 3.5, okay. So first of all, and what is 16 divided by 3? It is 5.33, right? So my breakaway point has to lie between -2 and 0. So if I choose this negative sign, it will be something less than -2, which is invalid. So I will only choose the positive sign. So if I choose the positive sign, this will be upon 2, that is 0.88 minus 0.88. But be careful, right? They have not asked you what is my breakaway point. They have asked you what is the value of k at breakaway point. So for that you have to put this value in this equation, right? So yeah, let me put in this equation. So it would be minus 0.88 cube minus 8 into 0.88 square minus 12 into 0.881 minus, which is 3.7. Okay, which is actually kind of incorrect. Okay, because according to me the range is given between 5, so something I'm doing something, but this is all correct, right? I'm getting the breakaway point in the correct location. What is going wrong? Just thinking, what can go wrong? Breakaway point location is correct. Let me think about this. Minus 0.8816 whole cube. Oh, sorry, there was a negative sign as well, right? I forgot to. Okay, forgot to add the negative sign. My bad. Okay. Minus 8 into. Hold on a second. Minus 0.8816 whole cube. This will be positive only. This will be minus 8 into 0.8816 whole square. And okay. This will be okay. Let me solve it like this only. Minus, so 0.8816 plus 2 into 6 minus 0.8816 into 0.8816. Here it comes correct. Maybe I don't know. I'm solving something wrong. Like here, I don't know, something I'm doing wrong. But ultimately, your k value will come out to be 5.04, which is in the range. For some reason, I was calculating. So be careful, right? Be careful with NAT. So k is coming out to be 5.04. This will be your answer for the question. Let's solve the next one. So here you have been given the root loci plot. A negative unity feedback system forward gun is given, k is varying from 0 to infinity. The correct transfer function, the transfer function g of s. Okay, so they have plotted it for k g of s. So basically they are asking you, not that they are asking you about the OLTF, open loop transfer function. So I see that there are 1 2 3 4 asymptotes, and I don't see, so okay, sorry, 5 asymptotes. There are 5 asymptotes, right? And they have not mentioned anything regarding the zeros. So basically number of poles minus number of zeros will always be 5. Okay, here it is true, here it is true, here it is true, here it is also true. So all of them are true. Here now few interesting things will happen. The angle of asymptote is also fine, right? This is also 36, 36. This is fine. Angle of asymptote is fine. But how else will I verify? So I see, right, all of them are going outwards. So basically all of them has to be pole, right? Because my root locus starts from open loop poles. So all of them are poles at the same location. So all of them are poles at the same location. Only this is satisfying it. Correct? Others are not satisfying. So this is also satisfying. All of them are poles. But here it is telling that I have a 0 at s equal to 1. But if I had a 0 at s equal to 1, then there will be a root locus, right? Plot like this. But there isn't. So I don't have a 0 at s equal to 1. So all these are wrong. Only this is correct. All I have the same pole, repeated pole at s equal to -1. Very good question. Okay, let's solve the next question. Let's solve the next question. Okay, so yeah, let me solve the next question. So this is the next question. Consider the closed loop system. Shown. This is a closed loop system. OLTF is given, k is given. The root locus for the closed loop system is drawn from 0 to infinity. The angle of departure between 0 to 360 of the root locus branch drawn from the pole -1 plus j2. So basically they are asking me what will be the angle of departure for this particular pole, right? So let me first of all plot the root locus. So I will have basically, right, so I know the real parts of my zeros. What are the real parts? So my zeros are also are, it seems my zeros also are complex, right? B square minus 4ac, B square minus 4ac. All the both these poles are complex. Okay, so I know that. Okay, let me calculate it. What is the pole location? What is the zero location? Zero location is minus b plus minus b square that is 4 minus 4ac, that is minus 8 upon 2a. B square minus 4ac. 1 plus minus j. Okay, so I will have two zeros at 1 plus j and 1 minus j. What about poles? So I will have pole minus b plus minus b square minus 4ac. This will be minus 2 plus minus j4 upon 2, that is minus 1 plus minus j2. So yeah, minus 1 plus minus j2, so minus 1 plus minus j2 will be somewhere here. Okay, this will be minus 1 plus 2j, and this will be minus 1 minus j2. So now they are asking me what will be the angle of departure for this particular pole, right? This pole is lying here. So how do I calculate the angle of departure? Angle of departure, the formula of the root locus for angle of departure for a normal root locus, it is 180 plus theta z minus theta p, because it was for pole, minus theta p. So what is the angle of departure here? It is plus 90, right? So this is plus 90. I have only a single pole. What about the angle of departure here, right? So what is this angle? This angle, what is the distance, x distance? It is simply, this is minus 1, right? This is plus 1. So the x distance is actually 2. What is the y distance? This is plus 2. This distance is 1. So this y distance would be 1. So your this theta angle would be tan inverse 1 upon 2. So tan inverse half. What is tan inverse half? So tan inverse half is 26.86, but there is my theta. This angle would be 180 minus theta, right? So 180 minus theta, this would be 153.43. And what will be the angle contributed by this? Angle contributed by this, right? We have to calculate this. So what is the height? Okay, just hold on. What is the height here? Let me choose this. This, right? This angle. So for this triangle, again let me write this as theta 2. What is the height? This height actually is, diagram is messy, but I hope you will be able to figure out. This height would be 4. Okay, and this height, this x distance, right, would be same. This will not change. This is 1. So this theta will be tan inverse 1 by 4, but your overall this angle will be 180 minus tan inverse 1 by 4. So 180, the tan inverse 1 by 4, then 180 minus this, so it will be 165. Okay, did I forget to write this? No. Okay, plus 166 basically. So your angle of departure theta d would be, right, it will be 165 plus 153.43 plus 180 minus 90, which is coming out to be 409. But they have asked you between 0 to 360. So what I can do, subtracting 360 or adding 360, it won't make any difference. So I can subtract 360, correct? If I subtract 360, okay, something is wrong because answer is not matching. I'm doing some mistake. This distance is okay. Sorry, this is not 1, right? This is 2 distance. Sorry, this is 2 distance. This is not 1. So it will be actually, this height will be what? How much? This height would be, this is 1, right? This distance is 1, and this much is 2 actually. This height is 2. Sorry. So like you will be able to figure it out. This height will be 3 actually. Sorry about that. And this triangle distance will be 2. So actually, sorry. I'm extremely sorry, this angle is not correct. So it will be tan inverse. I'm not explaining because I hope you will be able to figure out how to calculate this angle, right? That much aptitude we have. Okay, so this angle would be yep. Let me I know you guys will scream and you'll say sir ने अच्छे से बताया नहीं, sir ने समझाया नहीं, ठीक है, एग्जाम आ रहा है, sir ने समझाया नहीं. Okay, let me keep it clean. Let me keep it clean. Okay. Yeah, let me keep it clean. Now you will not complain, right? इतना हार्ड वर्क करते हो फिर भी लाइक कमेंट तो कुछ करते नहीं हो, ठीक है, सपोर्ट भी नहीं करते, शेयर भी नहीं करते वीडियो. ओके, सो yeah, this will be sigma, this will be j omega. So I have two zeros over here, right? So this zero location is -1, sorry, +1 plus j. This zero location is -1 minus, sorry, +1 minus j. I have a pole, let me keep it a bit down, pole at this and this location, -1 plus 2j, right? -1 plus 2j, correct? And -1 minus 2j. Correct. So yep, so basically yep, if I solve this right now, what is the, this angle is, I think this angle is not that difficult for you to understand. This will be 90, right? That is gone. So theta p, summation of theta p is 90. I have to compute the summation of theta z. So for that I have to compute this angle. Let me first compute this one, the easier one. This we have already computed. So let me assume this as a triangle, right? So what is this distance? So this point, right, this much distance is how much? 1. Real part is 1, right? This is -1. 1. This is distance is 1. And although it is not to scale, but this much distance is also 1, right? Real part is 1. So overall the distance would be 2. So this distance is 2. So triangle has a base of 2. What is the height? So this is plus j2. Okay, here j2, right? And this is actually j. So what is this distance? 1. So now this is the theta. So from here we actually calculate 180 minus theta. So one of this angle is correct. This angle is 153.43. That is absolutely correct. But this one was incorrect. So now what is this triangle? Right. So this much height is again 1 and this much height was 2, right? Because it is at 2j. So this overall height would be 3. But this x distance is same, right? Here also it is same, that is 2. So that's why it will be, this is my theta, but actually I want to compute 180 minus theta. So this would be tan inverse 2 upon 3, right? So 2 upon 3, sorry, not 2 upon 3, 3 upon 2, tan inverse 3 upon 2, 180 minus theta, which is 123.69. okay. So now if I add, so now my angle of departure would be actually, this would be 123.69 plus 153.43 plus 180 minus 90, sorry, not minus 180, why 180, sorry, minus 90, okay, which comes out to be 367.12 degrees. Now they have asked in the range of 0 to 360. So what I will do, I will subtract 360 because adding and subtracting 360 does not make any difference. So if I subtract this 360, my answer will be 7.12. So this will be your answer for the question. That's it. Okay, in degrees, remember they have asked in degrees, so you will solve in degrees. So yeah, these questions are good. Next question, we have this question, right? Consider a unity negative feedback system with open loop pole zero map shown, s if s equal to j alpha, basically this axis, it is lying where alpha is greater than 0, lies on the root locus. The value of alpha would be, what is the value of alpha? Basically it is asking me what is the crossover point wherever it is intersecting the j omega axis, because if I plot the root locus, there will be a breakaway point, right? So maybe it will break like this. There will be two branches. Okay, sorry, no, I think it will go like this. There will be three branches, right? Because there are three poles, there will be three branches actually. So one root locus will go like this, other root locus will go like this, and the third one will go like this, right? There will be three virtual zeros. So basically they are asking me this point, right, wherever it is intersecting. So okay, that is interesting. Okay, I only know the pole zero map, so pole zero map I know, right? So it is basically k upon, my g of s is k upon s plus 4 s plus 1. Let me solve it. This, right, it has to satisfy this. So I can check the angle condition, right? So basically the angle of g of s at s equal to j omega or j alpha must satisfy 180 degree, right? It has to satisfy 180 plus 180 or minus 180, whichever one is fine, both are same. Okay, so this would be if I put, this is my g of s, right? So this would be if I put s equal to j alpha k upon j alpha plus 4 j alpha plus 4 and j alpha. So what is the angle? So angle contribution due to just j alpha will be minus 90. Angle contribution due to this will be tan inverse alpha by 4, and sorry, this one of them will be j alpha plus 1 actually, and due to the other one would be tan inverse alpha. Now this has to be equals to plus 180 or minus 180. I can choose minus 180 because everything is negative, so it's easier for me to choose minus 180. Both are same. So actually what happens is your tan inverse alpha plus tan inverse alpha by 4 is equals to 90. So there is a beautiful condition. What is the beautiful condition? If tan inverse x plus tan inverse y equals to 90 or pi by 2, then we say x into y will be equals to 1. How? Just derive, I hope you remember what is the expansion of tan inverse x minus plus tan inverse y. There was a formula, right, which was I think x minus y divided by 1 minus x plus y, whatever it was, right? So by that this, like this comes actually, okay, this comes from that formula, so derivation basically. So x into y equals to 1, so that means this into this will be equals to 1, so alpha into alpha by 4 will be equals to 1, okay. So alpha square equals to 4, alpha is a positive number, so alpha will be 2, alpha can be plus minus 2, but as alpha is positive number, so alpha has to be 2, so 2 will be your answer for the question. That's how simple it is. Like these tricks you should know in the exam hall, you can use it, but otherwise you are always welcome. That if you remember, the expansion of tan inverse x plus tan inverse y was actually equals to tan inverse x plus y upon 1 minus xy. I think something like this was there, right? And we know that 90 degree is nothing but tan inverse of infinity. That means this has to go to 0. That's why the denominator is going to 0. I'm explaining in a fast manner because this is not supposed to be explained by me. That's why. Okay, yeah, but still I'm doing it. So let's solve this next question. Consider the unity feedback negative feedback root locus where k is greater than or equals to 0. The root locus of this system is shown also, okay. The values of k will forward values of k, the system will have a pole at -1 plus j, okay. Forward value of k, I will have a pole at -1 plus j point. Okay, minus 1 plus j point. So minus 1 j point actually lies here, right? Minus 1 plus j will lie here, which is never in the root locus. Okay. Minus 1 j point, that is my root locus, and minus 1 plus j is lying here, and k is always positive, right? For all positive values of k, we have plotted the root locus. So for no positive value of k, right, it will never lie, basically, right? So basically, this was a like laddu question for no positive value of k, right? You can see from the root locus, for no positive value of k, it will lie in the root locus. So option C will be your correct answer for the question. Let's solve the next question. So yeah, this is the last question, I guess. Yep. So the open loop transfer function of the system shown in the figure is this. Okay. For k greater than equals to 0, which of the following real axis points is slash r on the root locus? Okay. Okay, which are the real axis point are on the root locus? So very simple, right? Let me plot the root locus. So just for the real axis, so pole 0 diagram, I have a 0 at s equal to 0, I have a 0 at s equal to minus 2, I have a 0, I have a pole at s equals to minus 5, and I have a pole at s equals to minus 7. So if I just plot on the real axis, right, this is a normal negative feedback system, so these two will meet. Okay, there will be some break in actually, and these two also will meet. Like you can plot the root locus, right? There will be two branches, and that's it. This will be my root locus. So they're asking me which is the valid point on the root locus in the real axis. So s equal to minus 1, s equal to minus 1, yes, it will lie on the root locus. So this is valid. S equal to minus 4, s equal to minus 4 is between minus 5 and minus 2, which is, there is no point on the root locus, right? S between this, right? So it is not valid. S equal to minus 6, yes, it is lying between minus 7 and minus 5, so it is valid. S equal to minus 10, again, if I see, it is not lying on the root locus, so it is invalid. So A and C will be your answer for the question. Okay, that was simple. The questions are from root locus. So with this, we end our root locus and we end our part 2. If you have enjoyed, again, the same thing, Dakshina. So like the video, comment down below, and yeah, I will meet you in the part 3 where we will discuss about frequency response. That is also a very important portion. So that's it from my end. Until then, happy learning.